Imagine a universe so vast, so intricate, that it contains billions of galaxies, each with its own cluster of stars, planets, and untold mysteries. Yet, this is just the beginning of our journey, an exploration into the depths of the cosmos, where the origins of stars, the elegant dance of planets, and the intricacies of life itself beckon us to seek answers. The universe, an unfathomably complex and ever-expanding realm, invites us to unravel its secrets, from the birth of the first celestial bodies to the evolution of consciousness, guiding us on a quest to understand our place in this boundless expanse. The origin of the universe, a subject that has captured the imagination of scientists, philosophers, and thinkers for centuries, continues to drive our pursuit of knowledge. One of the most enduring and widely accepted explanations is the Big Bang Theory, which proposes that around 13.8 billion years ago, the entire universe began as an infinitesimally small, incredibly hot and dense singularity. From this singularity, an explosive expansion set the stage for everything we know today. It wasn't an explosion in the conventional sense, but a rapid stretching of space itself, a phenomenon that created time, matter, and the fundamental forces of nature in the blink of an eye. As the universe expanded, it cooled, allowing protons and neutrons to form mere minutes after the Big Bang. These elementary particles began to combine into the simplest elements, primarily hydrogen and helium. Over millions of years, these elements, bound together by the force of gravity, eventually coalesced into the first stars and galaxies. In those early moments, the universe was a dark, empty void, punctuated only by vast clouds of gas and dust. But as stars ignited, their nuclear fusion created heavier elements, enriching the cosmos with the building blocks for planets, galaxies, and ultimately the conditions for life itself. Among the most significant pieces of evidence supporting the Big Bang Theory are the cosmic microwave background radiation and the redshift of distant galaxies. The cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, permeates the entire universe. It serves as a relic of the universe's infancy, providing a glimpse into its hot and dense origins. Discovered in the 1960s, this faint glow offers a snapshot of the universe just 300,000 years after its birth, revealing the conditions that led to the formation of galaxies and stars. Additionally, the redshift of galaxies, observed by astronomers like Edwin Hubble in the early 20th century, shows that galaxies are moving away from us. The farther a galaxy is, the faster it appears to be receding, a phenomenon that aligns perfectly with the expanding universe and the idea of an explosive origin. Yet the Big Bang Theory is not the only explanation for the universe's birth. There are competing models that refine or challenge its framework. One such theory is the inflationary model, which suggests that in the moments immediately following the Big Bang, the universe underwent an incredibly rapid period of expansion. This inflationary phase would have smoothed out any irregularities in the early universe, leading to the remarkably uniform cosmos we observe today. While much about this inflationary phase remains speculative, it offers insights into the initial conditions of the universe, shedding light on how the first moments of the cosmos unfolded. As our understanding deepens, some theorists have ventured further, proposing the possibility of a multiverse, a vast, perhaps infinite collection of universes, each governed by its own set of physical laws. If true, our universe could be just one among many, a mere slice of a much larger and more complex reality. This concept challenges the very nature of our understanding, suggesting that what we perceive as the entirety of existence may be just a small fraction of a grander, more intricate tapestry of realities. The idea of the multiverse raises profound questions. Is our universe unique, or are there countless other realms, each with its own version of reality? If the multiverse theory holds, it would revolutionize not only our understanding of the cosmos, but also our place within it. The Big Bang Theory, alongside the inflationary model and the concept of the multiverse, is part of an ongoing effort to explain not only how the universe came into being, but also how it continues to evolve. This exploration of the cosmos, however, is not purely scientific. It touches on philosophical and theological questions that have fascinated humanity for millennia. The origins of the universe are not just a matter of physics and cosmology. They are also deeply intertwined with metaphysics, prompting us to consider the very nature of existence itself. The universe as we know it is an ever-changing, expanding entity. The evidence supporting the Big Bang theory, cosmic microwave background radiation, the expansion of galaxies, and the discovery of new phenomena has propelled our understanding of the universe's birth and evolution. However, this is only the beginning. As we continue to probe deeper into the cosmos, with new technologies and innovative theories, we are continually expanding the boundaries of human knowledge. The more we learn about the universe's origins, the more we are confronted with its complexity and its vastness, challenging us to contemplate not just how it began, but how it will evolve and what our place within it is. The journey of exploring the universe's beginnings is far from over. Each new discovery, each breakthrough opens up more questions than answers. Yet it is this very uncertainty, this insatiable curiosity, that drives us forward. From the birth of stars to the formation of galaxies, from the depths of black holes to the exploration of distant exoplanets, humanity's quest for knowledge is far from complete. As we venture into the unknown, we are reminded of the vastness of time and space and the infinite possibilities that lie beyond the horizon, waiting to be discovered. We begin by examining the abundance of light elements like hydrogen, helium, and lithium throughout the universe. These elements, found in large quantities, strongly align with predictions made by the Big Bang model. According to this theory, these elements were formed in the first few minutes after the Big Bang during a phase known as Big Bang nucleosynthesis. The exact proportions of hydrogen, helium, and lithium that we observe today in the cosmos match what the theory anticipates, further strengthening the case for the Big Bang. This alignment between theory and observation provides critical validation of the model. In addition to the chemical evidence, advances in technology have enabled scientists to probe the structure of the universe on a cosmic scale. By studying the distribution of galaxies and galaxy clusters, researchers have discovered patterns that suggest the influence of dark matter and provide insights into the initial conditions of the universe. These observations, which span the largest scales of space, complement the Big Bang model and help form a coherent framework for understanding the universe's past. Together, these compelling lines of evidence create a robust argument for the Big Bang theory, offering a vision of the universe as dynamic, evolving, and deeply historical. However, despite these advancements, profound questions still linger regarding the earliest moments of the universe's existence. The first few minutes after the Big Bang are particularly enigmatic, holding mysteries that continue to captivate scientists and cosmologists. One of the most perplexing questions concerns the nature of the Big Bang itself. We know that the universe began as an extremely hot and dense point. But what triggered the initial expansion? This moment remains elusive, prompting researchers to explore various concepts such as quantum fluctuations, which might have sparked the inflationary expansion. Equally mysterious are the phenomena of dark matter and dark energy, which together account for around 95% of the universe. Though dark matter exerts gravitational forces that influence the motion of galaxies and clusters of galaxies, its precise nature remains unknown. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe, yet its properties and origins are still shrouded in uncertainty. Deciphering the mysteries of dark matter and dark energy could provide us with the keys to unlocking a deeper understanding of the universe's early dynamics. Additionally, the conditions during the universe's first moments are the subject of much speculation. Scientists have developed theories regarding how elements like hydrogen and helium were formed just minutes after the Big Bang. However, the exact processes and interactions that occurred during Big Bang nucleosynthesis are still not fully understood. Researchers are tirelessly working to refine their knowledge of these early processes, as they are the very foundation upon which stars and galaxies formed billions of years later. Adding complexity to the picture is the theory of cosmic inflation. According to this theory, in the tiniest fraction of a second after the Big Bang, the universe expanded at an exponential rate. This inflationary period offers solutions to several puzzles concerning the large-scale structure of the universe. Nevertheless, the specifics of what drove this rapid expansion and how it fits within our understanding of particle physics remain subjects of intense investigation. Each new discovery brings us one step closer to uncovering these cosmic mysteries, while simultaneously revealing the intricate and awe-inspiring tapestry of the universe's early history. One of the most powerful tools scientists use to explore the origins of the universe is the study of cosmic microwave background radiation, or CMB. This faint, pervasive glow is a relic from the early universe, dating back to when the universe had cooled enough for atoms to form, about 380,000 years after the Big Bang. As the universe continued to expand, this radiation stretched and cooled, allowing it to be captured and analyzed by modern instruments. To study the CMB, scientists rely on sophisticated telescopes and satellites, one of the most significant of which was NASA's Wilkinson Microwave Anisotropy Probe, a WMAP, launched in 2001. This satellite mapped minute fluctuations in temperature and polarization across the entire sky, providing detailed insights into the density variations present in the early universe. These observations offer a snapshot of the primordial conditions, enabling researchers to refine their understanding of the universe's expansion and structure. The data collected from CMB studies has revolutionized our understanding of cosmology. The temperature fluctuations observed in the CMB correspond to areas of varying matter density, providing crucial insights into how galaxies and large-scale structures formed. In addition, the CMB carries hidden clues about the overall composition of the universe. These findings have revealed a surprising balance between ordinary matter, and dark energy, suggesting that only about 5% of the universe is made up of the atoms that form stars, planets, and living beings. The remainder is dominated by dark energy and dark matter, elements that continue to intrigue and mystify scientists. Together, these breakthroughs in our understanding of the universe's early history paint a picture of a cosmos far more complex and wondrous than we ever imagined. While many questions remain, each new discovery inches us closer to unraveling the greatest mysteries of the universe. The cosmic microwave background, CMB, stands as one of the most profound pieces of evidence in our quest to understand the origins of the universe. It is not merely a relic of the past, but a cosmic fingerprint, capturing the earliest moments of the universe's existence. The CMB has not only provided a snapshot of the infant cosmos, but has also bolstered pivotal theories like inflation. According to the theory of inflation, the universe expanded exponentially in a fraction of a second right after the Big Bang, stretching from subatomic scales to vast dimensions. This rapid expansion would have left behind subtle imprints on the cosmic backdrop, which scientists have painstakingly studied over decades. These imprints, remarkably uniform in nature, reinforce our understanding of the universe's early moments, confirming ideas that once seemed speculative. As we continue to analyze this ancient radiation, new technologies are ushering in a new age of discovery. These advancements promise to reveal even deeper insights, challenging not only our current knowledge, but the very assumptions that have shaped cosmology for centuries. The questions we ask now may fundamentally alter how we perceive the cosmos, revealing its vast and enigmatic nature in ways we have yet to imagine. One of the most profound and elusive questions in modern cosmology revolves around the nature of time and space itself. What existed before the Big Bang? It's a question that seems almost impossible to answer, for the Big Bang represents the moment when the universe began to expand, a moment that occurred approximately 13.8 billion years ago. But here's the catch. Time and space, as we know them, only began with the Big Bang. That makes it extraordinarily difficult, if not impossible, to conceptualize a time before time itself. How could we, as creatures bound by the flow of time, even begin to imagine a reality that existed before the beginning of time? Some intriguing theories have emerged to address this very question. One such theory is the cyclic universe model, which posits that the universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang might not have been the definitive beginning, but rather a transition from an earlier phase of the universe, a cosmic rebirth. According to this model, the universe may have collapsed in on itself, forming a singularity, only to undergo another Big Bang and begin the cycle anew. In essence, the cosmos may be locked in a never-ending dance of birth, death, and rebirth. Then, there are the quantum interpretations, which suggest that space and time behave radically differently at extreme scales. Some theories propose that time, as we understand it, may not even exist before the Big Bang. If time is a product of the Big Bang, then perhaps the very concept of before is irrelevant. This notion stretches the limits of our understanding, forcing us to reconsider the nature of existence itself. Could it be that the universe, in its primordial state, existed in a form so alien to our perceptions that it defies our conventional understanding of reality? Yet, despite these fascinating hypotheses, we currently lack definitive evidence to confirm what, if anything, existed before the Big Bang. This remains one of the most tantalizing puzzles in science, and as our tools and theories evolve, we may one day be able to peer beyond the veil of time, uncovering answers that reshape our understanding of the cosmos. Until then, scientists continue their relentless pursuit of knowledge, exploring the furthest reaches of space and the deepest corners of theoretical physics. The quest for answers continues to captivate not only scientists, but anyone with a curiosity about the vast unknown, urging us all to look beyond the edges of the known universe and into the infinite. In the aftermath of the Big Bang, the universe underwent a dramatic transformation, with the formation of galaxies marking a crucial milestone in its evolution. The universe, initially in a hot and dense state, was a seething cauldron of particles and radiation. As it expanded and began to cool, slight fluctuations in the density of matter allowed regions of space to clump together. These clumps, composed primarily of hydrogen and helium, acted as the seeds from which galaxies would eventually grow. Over millions of years, these regions began to condense under the influence of gravity, eventually coalescing into the first galaxies. But the story didn't end there. As galaxies formed, they didn't remain isolated. They were drawn toward one another by their mutual gravitational attraction. Over time, this gravitational pull led to a variety of galaxy types. Some galaxies evolved into spirals, like our own Milky Way, with their iconic winding arms wrapped around a central bulge. Others took on a more elliptical shape, smooth and rounded without the distinct structure of spiral galaxies. And still others grew into irregular shapes, lacking the symmetry of their more orderly cousins. Each galaxy, regardless of its shape, is a critical component in the larger cosmic story. Galaxies are not just collections of stars. They are dynamic, living entities that are constantly evolving. Within their vast expanses, stars are born, live, and die, with their life cycles playing a fundamental role in the larger processes of galactic evolution. When a star dies, it releases its materials into the interstellar medium, enriching the surrounding space with heavier elements. These elements, forged in the hearts of stars, become the building blocks for the next generation of stars, planets, and possibly life itself. This cycle of birth, death, and rebirth is central to the evolution of the cosmos. Galaxies, in their ever-changing states, form the backdrop for the formation of planetary systems and ultimately life. In this way, galaxies are not just passive collections of matter. They are the architects of the universe, shaping the very fabric of existence and setting the stage for the creation of new worlds. It is within galaxies that the ingredients for life as we know it are mixed, refined, and scattered throughout the universe, ready to begin the process again in distant corners of the cosmos. Galaxies, those vast collections of stars, gas, dust, and dark matter, are the heartbeat of the universe, influencing and interacting with each other through the powerful force of gravity. These gravitational forces lead to phenomena that not only shape the galaxies themselves, but also reshape the larger structure of the cosmos. Collisions, mergers, and other galactic interactions are common, and they have profound implications for the universe's evolution, often altering the very fabric of space itself. However, the significance of galaxies stretches far beyond their individual components. They serve as natural laboratories for astrophysical processes, offering us valuable insights into the birth, life, and eventual death of stars, and the formation of cosmic structures. Every galaxy is a living record of the universe's history, from the earliest moments after the Big Bang to the ongoing processes that continue to shape our cosmic environment. The study of galaxies, in particular, provides critical clues about some of the universe's greatest mysteries. It sheds light on the nature of dark matter, the ever-expanding universe, and the formation of large-scale structures that span billions of light years. In a sense, galaxies are the fundamental building blocks of the cosmos. each one contributing a unique chapter to the cosmic story. By studying them, scientists not only glimpse the past, but also unravel the future of the universe itself, helping to answer some of the most profound questions humanity has ever asked. Among the most perplexing aspects of the universe are dark matter and dark energy, two invisible and yet overwhelmingly dominant forces that together account for approximately 95% of the total mass energy content of the cosmos. To put this into perspective, all the visible matter we can observe, stars, planets, galaxies, makes up only a small fraction, about 5%. This stark contrast between the visible and the unseen drives scientists to delve deeper into the nature of these elusive substances, to understand their role and their mysterious behaviors. Dark matter, for example, is thought to be a type of matter that doesn't interact with light, making it undetectable by traditional telescopes. Instead, its presence is inferred through its gravitational effects on visible matter. Galaxies, for instance, spin at speeds that, without the gravitational pull of dark matter, would cause them to fly apart. This unseen mass is believed to help anchor galaxies together and even play a role in shaping the large-scale structure of the universe. Despite decades of research, scientists have yet to pinpoint the exact particles that make up dark matter. Proposals for potential candidates, such as weakly interacting massive particles, WIMPs, have yet to be confirmed, leaving the search for dark matter one of the most exciting frontiers in modern astrophysics. On the other hand, dark energy remains even more baffling. This mysterious force is thought to be responsible for the accelerated expansion of the universe. While gravity pulls objects together, dark energy pushes them apart, driving galaxies further and further away from each other. This has profound implications for the long-term fate of the universe. If dark energy continues to dominate, we may witness a future in which galaxies drift ever farther apart, leading to a cold, diffuse cosmos. In many ways, dark matter and dark energy force us to reconsider everything we thought we knew about the laws of physics. Their existence challenges the very foundations of our understanding of the universe, and the mysteries surrounding them promise to transform the way we see the cosmos in the years to come. Among the most enigmatic and awe-inspiring entities in the universe are black holes. These colossal gravitational wells have the power to reshape space-time itself and influence the very behavior of nearby stars and gas. Their formation typically begins with a massive star, which, after exhausting its nuclear fuel, collapses under its own gravity. The outer layers of the star are expelled in a cataclysmic explosion known as a supernova, leaving behind a core so dense that not even light can escape, creating what we call a black hole. Black holes come in various sizes. The most common are stellar black holes, which form from individual stars, but at the centers of galaxies, including our own Milky Way, lie supermassive black holes, colossal entities that can be millions or even billions of times more massive than the Sun. Current theories suggest that these supermassive black holes formed through the gradual merging of smaller black holes and the accumulation of vast amounts of gas and dust over the course of billions of years. Surprisingly, black holes are not merely cosmic vacuum cleaners. They play a critical role in shaping galaxies. The supermassive black holes at the centers of galaxies can influence the rate of star formation, regulate the distribution of matter, and even emit powerful jets of energy that interact with the surrounding gas clouds, triggering the birth of new stars. These interactions make black holes essential players in the ongoing evolution of galaxies, driving the very processes that create the stars and structures we observe in the universe today. Neutron stars, another fascinating component of the cosmos, present a different set of challenges to our understanding of physics. These dense remnants of massive stars that have exploded in supernovae are incredibly compact, with masses greater than the Sun but squeezed into a sphere only about 15 miles in diameter. This extraordinary density means that a single teaspoon of neutron star material would weigh as much as a mountain range on Earth. It's this extreme density that challenges our understanding of matter under such intense conditions. One of the most intriguing features of neutron stars is their composition. These stars are primarily made up of neutrons, which are subatomic particles that have no electric charge. Inside a neutron star, the pressure is so immense that protons and electrons combine to form neutrons. The conditions within these stars are so extreme that they push the boundaries of modern physics, challenging our current theories of quantum mechanics and nuclear physics. The behavior of matter in these environments remains one of the great unsolved mysteries in science. In addition to their extreme density, neutron stars often possess incredibly strong magnetic fields, some 1,000,000,000 times stronger than Earth's magnetic field. In certain cases, neutron stars emit beams of radiation from their magnetic poles, creating a phenomenon known as pulsars. These rapidly spinning stars send beams of radiation sweeping across space, much like the beam of a lighthouse. Pulsars are not only fascinating objects in their own right, but also valuable tools for scientists. They help test and refine theories of gravity and provide crucial insights into the very fabric of space-time. Together, these celestial objects, galaxies, dark matter, dark energy, black holes, and neutron stars, offer a glimpse into the deepest workings of the universe. They challenge our understanding of the cosmos and force us to confront questions about the nature of reality itself. As scientists continue to study these phenomena, new discoveries are bound to emerge, pushing the boundaries of human knowledge and reshaping our view of the universe. Moreover, neutron stars serve as some of the most extreme and intriguing laboratories for investigating the nature of matter under conditions that defy the known laws of physics. Within the dense interiors of these stellar remnants, the interactions and pressures present push the boundaries of what we understand about the universe. This unique environment not only challenges existing theories, but it also opens doors to groundbreaking research, particularly in the pursuit of unraveling the mysteries of dark matter. As we delve deeper into the enigmatic characteristics of neutron stars, we are confronted with profound questions about the very fabric of reality and the forces that govern the cosmos. Each new discovery reveals a new layer of complexity, offering the potential to radically shift our understanding of the universe and reminding us how much we still have to learn. Massive cosmic events, such as supernovae, are crucial elements in the life cycle of stars. They act as the universe's natural recycling mechanism, giving birth to the next generation of stellar bodies. When a massive star reaches the end of its life, it can undergo a catastrophic explosion, an event so brilliant that it temporarily outshines entire galaxies. This dramatic phenomenon, known as a supernova, signifies not just the death of a star, but the dispersal of its elements across vast stretches of space. In these final moments, a star releases a torrent of elements forged within its core over billions of years. For instance, nuclear fusion within a star creates heavier elements like carbon, oxygen, and iron, which are then expelled into the interstellar medium during the supernova explosion. These elements serve as the essential building blocks for new stars, planets, and eventually life itself. But the impact of a supernova stretches far beyond the mere creation of elements. The shockwaves produced by the explosion propagate through space, sending ripples across nearby gas clouds, triggering their collapse and sparking the formation of new stars. This cyclical process highlights the interconnectedness of life and death in the universe, where the demise of one star can lead to the birth of many others. Supernovae are, in essence, the universe's way of recycling its material, enabling the ongoing evolution of galaxies. These events enhance the chemical diversity of the cosmos, and the resulting nebula, clouds of gas and dust, become fertile grounds for star formation. In these regions, gravity pulls material together, eventually igniting the birth of new stars. Thus, the dramatic end of a star's life gives rise to new cosmic entities, underscoring the ongoing cycle of creation and destruction that shapes the universe. Gravitational waves, first predicted by Albert Einstein over a century ago, have revolutionized the way we observe and understand the cosmos. These ripples in the very fabric of space and time, produced by the most violent and energetic events in the universe, such as colliding black holes or merging neutron stars, provide an entirely new method of studying the universe. Unlike traditional telescopes, which rely on detecting light, gravitational waves offer a novel sense of hearing the cosmos, allowing us to observe phenomena that were previously invisible to our instruments. This breakthrough has opened up a new frontier in astrophysics, offering insights into some of the most elusive and mysterious processes in the universe. One of the most groundbreaking discoveries made through the detection of gravitational waves has been the observation of black hole mergers. When two black holes spiral inward and eventually collide, they release enormous amounts of energy in the form of gravitational waves, which can be detected by observatories like LIGO and Virgo. This phenomenon has confirmed the existence of black holes merging to form even larger black holes, validating a key prediction of Einstein's general theory of relativity. The discovery has not only deepened our understanding of black holes, but also sparked new questions regarding their formation, populations, and the role they play in the evolution of galaxies. Moreover, gravitational wave astronomy has provided stunning revelations about the origins of heavy elements in the universe. In 2017, the detection of gravitational waves from a neutron star merger was accompanied by the observation of a brilliant burst of electromagnetic radiation. This event also scattered trace amounts of heavy elements, such as gold and platinum, across the universe. This discovery supports the idea that neutron star collisions are critical sites for nucleosynthesis, the process by which the universe's heaviest elements are forged. This has reshaped our understanding of where some of the rarest and most precious materials on Earth originate, highlighting the intricate processes at play during these cataclysmic events. The study of gravitational waves has ushered in a new era of astronomy, one that complements traditional methods of observing the universe through the electromagnetic spectrum. By studying these ripples in space-time, scientists are peeling back the layers of the cosmos in ways that were once thought impossible. Gravitational wave astronomy holds the promise of revealing answers to some of the most profound questions in science, such as the true nature of gravity, the structure of space-time, and the very evolution of the universe itself. In the early 20th century, Albert Einstein's theory of relativity forever changed our understanding of space and time. Before Einstein's groundbreaking work, space was seen as an empty void in which events unfolded, and time was viewed as a constant, ticking away at a steady, predictable pace. However, the theory of relativity shattered these notions, proposing that space and time are intimately connected and that they are both shaped by the presence of mass and energy. This revelation opened up entirely new avenues of inquiry, allowing us to explore the mysteries of black holes, neutron stars, gravitational waves, and the very fabric of the cosmos. Today, Einstein's legacy continues to shape the way we explore the universe, and his theory remains one of the cornerstones of modern physics. Albert Einstein's revolutionary insights forever transformed our understanding of space and time. He introduced the notion that the two are not separate entities, but are intricately connected, forming a four-dimensional continuum known as space-time. This idea completely shattered previous conceptions about the nature of reality, showing that space and time are far from independent. They constantly interact and influence each other in ways that are both profound and difficult to grasp. One of the most mind-bending aspects of Einstein's theory of relativity is the realization that time is not a fixed, unchanging backdrop to human experience. In fact, time is relative and can be experienced differently depending on the observer's speed and gravitational environment. For instance, an astronaut traveling close to the speed of light will experience time at a much slower rate than someone on Earth. This phenomenon, known as time dilation, suggests that as the astronaut speeds up, the passage of time for them slows down dramatically compared to someone in a more stationary position. The most striking implication of this is that when the astronaut returns to Earth after their high-speed journey, they will have aged much less than those who stayed behind. This concept reshapes our entire understanding of aging and challenges our conventional notions of time. The very passage of time itself, once seen as a constant, is revealed to be as dynamic and variable as the universe around us. Relativity also introduced a stunning new perspective on the fabric of space. According to Einstein, space is not an empty void. Instead, it is a flexible, malleable entity that can be distorted by the presence of mass. Massive objects, like stars and planets, warp the space-time continuum, creating what we experience as gravity. This stands in stark contrast to Isaac Newton's theory of gravity, which posited that gravity was a force acting across vast distances. In Einstein's view, gravity is not a force, but the result of mass bending space-time itself. This twist in our understanding shows that massive objects like Earth or the Sun shape the very space around them, influencing how objects move through it. These ideas challenge our intuition in radical ways. They force us to reconsider everything we thought we knew about the universe, reminding us that space and time are not rigid, unchanging elements, but are instead dynamic, ever-shifting, and influenced by speed, gravity, and the very structure of the cosmos itself. Through the lens of relativity, we begin to appreciate the complex, interconnected nature of the universe, unveiling an intricate dance between space and time that deepens our understanding of reality itself. One of the most fascinating consequences of relativity and the bending of space-time is the theoretical concept of wormholes. These hypothetical structures capture the imaginations of physicists and cosmologists alike, representing potential shortcuts through space and time. Wormholes are sometimes envisioned as tunnels that could connect distant regions of space or even different moments in time, challenging our basic understanding of the universe's structure. The significance of wormholes extends far beyond their use as potential space-time shortcuts. They may offer profound insights into the very nature of gravity and the fabric of space-time. According to Einstein's theory of general relativity, massive objects can cause distortions in space-time that may lead to the formation of wormholes. This raises the tantalizing possibility that future civilizations might one day learn to harness these structures, that opening up new pathways for interstellar travel and revolutionizing our perception of space and time. Moreover, wormholes challenge traditional ideas of causality, specifically the notion that cause precedes effect. If wormholes can indeed connect different times as well as places, they provoke questions about the possibility of traveling backward or forward in time. This presents an entirely new set of paradoxes and theoretical complications, such as the famous grandfather paradox. If a time traveler were to prevent their own grandparents from meeting, would they erase their own existence from the timeline? While this concept of time travel remains largely within the realm of theoretical physics and science fiction, it sparks rigorous debates and fosters ongoing research. The study of wormholes may ultimately be key to unlocking deeper insights into the universe's fundamental laws and how they govern everything from the smallest subatomic particles to the vastest galaxies. Although there is no empirical evidence yet supporting the existence of wormholes, the theoretical models of such structures continue to inspire further exploration. These models serve as a gateway to understanding more exotic phenomena, such as dark energy and black holes, and may one day unlock some of the universe's most profound mysteries. The concept of time travel itself is an idea that has captivated human imagination for centuries. While the notion of traveling forward in time is theoretically possible, especially in light of Einstein's theory of relativity, traveling backward in time presents a more complex set of challenges. Einstein's theories suggest that time is not a constant, but rather something that can bend and stretch under the influence of gravity and speed. If someone were to travel at nearly the speed of light, they would experience time differently than someone at rest. For example, astronauts on a high-speed journey would age more slowly than people on Earth. This phenomenon, known as time dilation, has been observed and confirmed in experiments, such as those involving particles traveling at high velocities. Yet the concept of moving backward in time, reversing the flow of events, introduces paradoxes that stretch the limits of our understanding. Take, for instance, the grandfather paradox. What happens if a time traveler were to stop their grandparents from meeting? Could they undo their own existence? Such questions challenge the very notion of reality and causality. Many theorists have suggested that wormholes could provide a potential mechanism for time travel, offering shortcuts through space and time. However, while forward time travel is supported by the principles of relativity, backward time travel remains speculative, trapped in the realm of theoretical models and science fiction. Nonetheless, the possibility of time travel, whether forward or backward, continues to inspire both wonder and deep scientific inquiry, prompting us to ponder the fundamental nature of time itself. The expansion of the universe provides yet another lens through which we can reconsider our understanding of time. Traditionally, Time has been seen as a constant, a steady tick that continues regardless of the state of the cosmos. However, astronomers studying the universe's expansion have revealed a surprising connection between time and the ever-changing fabric of space. As the universe expands, it stretches the very wavelengths of light, altering how we perceive distant events. This phenomenon, known as redshift, occurs when light from galaxies or stars moving away from us shifts toward longer wavelengths, making the light appear redder. When we observe objects far away in space, we are not merely seeing them as they are in the present. Instead, we are looking back in time, seeing them as they were billions of years ago. This redshift, this stretching of light and space, fundamentally alters how we measure and interpret time across the universe. It reminds us that the passage of time is not a simple, fixed experience. Instead, it is intertwined with the fabric of space itself, constantly changing and adapting as the universe expands. This realization prompts us to reconsider everything we know about time, distance, and the nature of reality, inviting us to continue exploring the depths of the cosmos with fresh eyes. The expansion of the universe is more than just a scientific curiosity. It holds profound implications for the very fabric of time and space. As the universe continues to stretch out at an accelerating rate, distant galaxies are gradually moving beyond our observable horizon. This phenomenon suggests that in the far future, light emitted by these galaxies will no longer be able to reach us as they recede farther and farther away. This progressive expansion raises questions about the future of cosmic time itself. Time, which was once considered a fixed and unchanging constant, is now revealed to be dynamic, influenced by the vast scale of the universe's expansion. As galaxies move farther apart, especially those beyond a certain critical distance, they will slip out of our reach, leaving us unable to observe their light. This shift will fundamentally alter our understanding of the cosmic horizon. Previously, we viewed the universe's boundaries as a fixed point in time, a perspective grounded in the assumption that time itself was immutable. But with the accelerating expansion, we now realize that the cosmic horizon is a fluid and ever-shifting boundary. The growth of the universe not only reshapes the spatial structure of the cosmos, but also redefines the very nature of time, forcing us to reconsider our perceptions of reality within an evolving universe. This new understanding opens the door to a deeper exploration of the universe's origins, its fate, and the ultimate structure of existence. The ongoing expansion not only challenges the way we think about space and time, but invites us to reimagine our place in this vast, continuously changing cosmos. It compels us to confront profound questions about the universe's past, present, and future, making us question how time, once seen as linear and predictable, might bend, warp, and flow in ways we never before considered. Beyond this, the concept of the multiverse adds another layer of complexity to our understanding of reality. It proposes that our universe is just one of potentially infinite others, each governed by its own distinct set of physical laws and constants. This theory fundamentally challenges the very nature of existence, pushing us to reconsider not only our place in the cosmos, but also what it means for something to be real. If multiple universes do indeed exist, each with its own variations of physical conditions, it suggests that every possible event or outcome could manifest somewhere in this sprawling multiverse, adding depth to the idea that our universe is only one of many possible realities. One of the most fascinating implications of the multiverse theory is its potential impact on our understanding of free will and the nature of choice. In a multiverse with an infinite number of realities, each decision we make could result in the branching off of a new universe, with a different outcome emerging from each choice. This raises intriguing questions about the significance of our choices. Are our decisions as meaningful as we think, or are they just one version of countless possible realities? Some interpretations of this theory suggest that with every choice we make, the universe splits, giving rise to new branches of reality, each with a different outcome. This concept challenges traditional ideas about causality, consequences, and the narrative structure of existence, inviting us to contemplate the meaning of our experiences in a reality where every possible outcome exists in parallel. Furthermore, the multiverse theory offers a potential explanation for some of the most perplexing questions in cosmology, particularly the fine-tuning problem. The universe we observe is fine-tuned with remarkable precision. Its physical constants and initial conditions are set just right to allow for the existence of life. Even the slightest deviation from these values would render life as we know it impossible. The multiverse provides a possible solution. In a vast expanse of multiple universes, it is not surprising that at least one would develop the necessary conditions for life to arise. Instead of our universe being uniquely suited to life, it could simply be one among many universes where the right conditions happen to exist. The implications of the multiverse extend beyond just the theoretical. They raise profound questions about the nature of scientific inquiry and the limitations of human knowledge. If multiple universes exist, how do we study them? How can we develop methodologies to observe something that is, by its very nature, unobservable? This dilemma challenges our traditional scientific frameworks and forces us to think deeply about how we derive meaning and knowledge in a universe or multiverse that may be fundamentally unknowable in its entirety. It pushes the boundaries of what we consider to be science and urges us to reconsider how we define knowledge, existence, and reality itself. The concept of the multiverse invites us into a philosophical dialogue, pushing us to question the nature of our existence in a cosmos that may be far grander and more complex than we can ever fully comprehend. It asks us to imagine a reality that is infinitely larger than ourselves, where every possibility, every version of events is played out somewhere within an ever-expanding sea of universes. This idea forces us to reframe our understanding of who we are and where we fit within the grand scheme of the multiverse, expanding our vision of reality beyond what we thought possible. Turning from the cosmos to the very building blocks of existence, we find that the life of a star is born from the vast clouds of gas and dust that swirl throughout space. These nebulae are the remnants of ancient stars that have exploded, scattering their elements across the universe. As gravity pulls these scattered particles together, they form denser regions within the nebula. Over time, these clumps of matter grow larger, collapsing under their own gravity. As the material compacts, it increases in temperature and pressure until the core becomes hot enough for nuclear fusion to begin. At this stage, hydrogen atoms in the core collide and fuse, forming helium and releasing an enormous amount of energy in the form of light and heat. This marks the birth of a new star, one of countless others that have been formed in this manner over the eons. Our own sun, along with the myriad stars scattered across the night sky, was born in a similar process roughly 4.6 billion years ago. As the star continues to grow, the surrounding material from the nebula falls into the newly formed star, sustaining its energy output and fueling its brilliance. The early stages of a star's life are accompanied by a rotating disk of gas and dust surrounding the nascent star. This rotating disk is not just an afterthought. It plays a crucial role in the formation of planets, moons, and other celestial bodies. As material in the disk clumps together, it forms solid bodies, much like the process that formed the star itself. This process is how our own solar system came into being, with planets, including Earth, emerging from the same cloud of gas and dust that birthed the sun. Eventually, stars like our sun exhaust their hydrogen fuel, setting in motion a series of transformations that will lead to their ultimate demise. These changes mark the end of the star's active life, and though the specific details of this process depend on the mass of the star, all stars, from the most massive to those like our sun, face this inevitable fate. The life cycle of a star, from its birth in a nebula to its eventual death, reflects the dynamic and cyclical nature of the cosmos, where creation, transformation, and destruction are ongoing processes, shaping the universe in ways we are only beginning to understand. However, the legacy of a star's birth within the dense, colorful clouds of a nebula persists, continuing its journey through the vast cosmic cycle of stellar evolution. The star's formation serves as a vital contribution to the universe's intricate recycling process. Through the death and rebirth of stars, the universe perpetually enriches itself with the elements necessary for life, planting the seeds for new worlds. These stellar remnants remind us of the interconnectedness of cosmic events, where the ashes of dying stars breathe life into future generations of stars and planets. The process of planet formation, a cornerstone of this ongoing cycle, begins deep within vast, cold expanses of gas and dust. These molecular clouds, which stretch across light years of space, are primarily composed of hydrogen, helium, and trace elements. Over time, gravity, the invisible force that governs the universe, causes certain regions within these clouds to collapse under their own weight. As these pockets of gas and dust compress, they grow denser, eventually giving rise to a protostar at the center, surrounded by a rotating disk of material. This is known as the protoplanetary disk, the birthplace of planets. Within this disk, tiny particles begin to collide, stick together, and slowly accumulate into larger and larger bodies through a process called accretion. Initially, these are mere grains of dust, but as they continue to collide and clump together, they form planetesimals, small objects that can be the size of asteroids or even dwarf planets. Over millions of years, these planetesimals grow by attracting more material, aided by their increasing gravitational pull. Eventually, they may develop into protoplanets, larger planetary bodies that form the foundation of fully developed planets. The emergence of the young star itself plays a critical role in this process. As the star ignites and begins nuclear fusion, it begins emitting powerful solar winds that sweep through the protoplanetary disk, blowing away the remaining gas. This moment is pivotal because it can halt the growth of planets that have not yet formed or completed their development. As a result, the dynamics of the disk, combined with the strength of the star's radiation, can lead to vastly different planetary outcomes. Some regions of the disk, closer to the star, may form rocky planets, such as Earth, while those farther out may foster the formation of gas giants like Jupiter, which accumulate vast quantities of gas and ice. The forces at work within a star system are not confined to simple gravitational pull. Rather, the interactions between growing planetary bodies lead to a wide variety of outcomes. Collisions between planets can give rise to moons, while gravitational influences may cause certain planets to retain their material, while others get ejected into the cold reaches of space. The result is the incredible diversity of planetary systems we observe across the cosmos today, each one unique, with its own moons, rings, and celestial phenomena. Thus, the birth of planets is not a solitary event, but a complex cosmic dance. It is a blend of gravity, chemistry, and time that shapes the unique planetary systems across our galaxy. This process is far from instantaneous. It unfolds over billions of years. Starting with the remnants of star formation, the surrounding gas and dust gradually coalesce into a rotating protoplanetary disk. Within this disk, tiny particles collide and stick together, eventually growing into larger bodies, or planetesimals. These planetesimals then come together to form protoplanets, eventually giving rise to the planetary systems we study today. Several factors determine the course of planetary formation. One of the most influential is the type and mass of the star at the center of the system. A more massive star tends to produce a more robust protoplanetary disk, one that is hotter and more turbulent. The temperature of the disk plays a crucial role in determining where certain planets can form. In the warmer inner regions, rocky planets like Earth can form, while the cooler outer regions are where gas giants like Jupiter develop, accumulating vast amounts of gas and ice. The dynamics within the protoplanetary disk also play a key role in shaping the system. Turbulence within the disk can cause the gas and dust to clump together in various ways, leading to the formation of planets of varying sizes and compositions. Planetary interactions can further influence these formations. For instance, as planets grow, their gravitational interactions can drastically alter their orbits, resulting in planetary migrations or even catastrophic collisions. These interactions can shape the final arrangement of the planets in a system, creating a diverse range of configurations that we see across the universe today. Planetary evolution doesn't stop after the formation phase. Even after planets have formed, processes such as planet migration, where planets shift their orbits due to gravitational interactions, can reshape the entire system. Collisions between planets can further alter their positions and the makeup of the system. The presence of gas giants, in particular, can significantly influence the potential for life on terrestrial planets, as their gravity may either protect inner planets or, conversely, eject necessary materials from the system. Over time, these complex forces continue to evolve the system, adding layers of complexity to what might initially seem like a simple arrangement of planets. Protoplanetary disks are not just crucial to the formation of planets, they are also a window into the chemical composition and conditions under which these planets form. These disks often stretch vast distances, sometimes hundreds of astronomical units, and contain vital information about the early stages of planetary systems. The material found within them, gas, dust, and ice, can provide clues about where a planet is likely to form in relation to its parent star. For example, in the warmer inner regions, volatile substances like water vapor are likely to evaporate, while farther out, where temperatures are lower, ice and gas can accumulate, forming gas giants and icy bodies. Understanding the dynamics of protoplanetary disks allows scientists to piece together the history of planetary systems, both in our own solar system and beyond. The study of these ancient disks reveals the forces that shape planets and perhaps even the conditions that allow life to flourish. It is through these cosmic leftovers, fragments of stars long gone, that new worlds are born, and through this ongoing process, we catch a glimpse of our own origins in the vast expanse of the universe. The universe, with its vast, seemingly infinite expanse, is full of mysteries that continue to captivate humanity's imagination. One of the most intriguing aspects of our cosmic exploration is the study of protoplanetary disks. These dynamic, active environments are rich with turbulence and complex interactions. Such processes not only play a pivotal role in the formation of planets, but also influence the orbits of nascent worlds. Current astronomical observations keep a keen eye on these disks at different stages of development, aiming to unlock secrets about how planets, including those that may be capable of supporting life, come into existence. In doing so, these studies help us understand the essential conditions needed for life to emerge in diverse corners of the universe. The discovery of exoplanets, planets located outside our solar system, has completely transformed our understanding of the cosmos and our place within it. Before the 1990s, when the first exoplanet was confirmed, our view of the universe was largely confined to our solar system. We knew of the planets orbiting our sun, and that was the extent of our knowledge. But with the detection of these distant worlds, we were thrust into a new era. Today, we know that there are potentially billions of planets orbiting stars throughout our galaxy, each with its own unique properties. This newfound knowledge has forced us to reconsider many of our previous assumptions about planetary formation and the conditions required for life. Exoplanets come in an astonishing variety of forms, ranging from gas giants that dwarf Jupiter to rocky planets that might share similarities with Earth. This incredible diversity challenges the once conventional ideas of what is possible in planetary systems. As astronomers continue to identify such a wide array of exoplanets, it is becoming increasingly clear that our solar system is just one of countless others, each one holding its own distinct characteristics. This realization has given rise to a tantalizing thought. Could other habitable environments exist elsewhere in the universe? As we inch closer to answering that question, the search for extraterrestrial life has become an even more compelling pursuit. The methods we use to discover these exoplanets, such as the transit method and the radial velocity technique, offer critical insights into how we study celestial bodies. With advancements in technology, we are now able to detect even smaller and more distant exoplanets, including those that reside in the habitable zone of their respective stars, where conditions may be suitable for life as we know it. As these discoveries pile up, the universe seems more inviting and perhaps teeming with life in ways we could never have imagined. Each new planet found not only adds to the catalog of known worlds, but also deepens our understanding of Earth's origins and its possible future. These findings invite profound questions about our place in the cosmos. Could there be other intelligent beings pondering the same questions about their universe? Could there be other civilizations out there wondering if they are alone? The quest to answer these questions is an ongoing and exhilarating journey that continues to inspire curiosity and fuel scientific inquiry. The drive to uncover the possibility of life beyond Earth remains one of the most thrilling endeavors in modern science, drawing together fields such as biology, astronomy, physics, and technology. Scientists approach this search by first identifying environments that could potentially support life. Much of our understanding of life's resilience comes from extremophiles, organisms that thrive in some of the most extreme conditions on Earth. These organisms, which can survive in the deepest parts of the ocean in highly acidic environments or in places of intense radiation, have expanded our ideas of where life might exist elsewhere in the cosmos. The discovery of extremophiles has shown us that life may not require Earth-like conditions after all, but could also thrive in environments that we once thought inhospitable. Robotic space missions have become a critical part of this search for extraterrestrial life. Spacecraft and landers, such as the rovers exploring Mars, are equipped with advanced tools that allow scientists to analyze soil and rock samples for organic compounds and signs of microbial life. One of the most notable examples is NASA's Curiosity rover, which has spent years exploring the surface of Mars, seeking clues about past habitable environments. By studying areas that once hosted liquid water, an essential ingredient for life, we gain important insights into whether Mars or other planets could have supported life in the past or could potentially support it in the future. Another significant area of focus lies in the study of exoplanet atmospheres. Using powerful telescopes both on the ground and in space, astronomers can analyze the light passing through these distant atmospheres to look for biosignatures, molecules that indicate biological processes. Gases like methane and oxygen, especially when found in particular ratios, are key indicators of the potential for life. The James Webb Space Telescope, a cutting-edge instrument launched in recent years, is enhancing our ability to detect these signatures, providing a more detailed and expansive view of planets beyond our solar system. By examining the light from stars shining through distant atmospheres, scientists can infer the chemical composition of exoplanets and assess their potential habitability. In addition to the search for exoplanets, researchers are turning their attention closer to home, to some of the icy moons in our own solar system. Moons like Europa and Enceladus orbiting Jupiter and Saturn, respectively, are believed to have subsurface oceans hidden beneath their frozen crusts. These oceans, warmed by tidal forces and potentially rich in chemical nutrients, may offer the perfect conditions for life. Upcoming missions aim to drill through the ice and sample these oceans directly, taking us one step closer to answering the profound question, are we alone in the universe? With each discovery, our methods for exploration and detection continue to improve. The science behind the search for extraterrestrial life is becoming increasingly sophisticated, fueled by our unrelenting curiosity about the universe. Scientists believe that certain regions in our galaxy, such as specific exoplanets, moons, and other locations with Earth-like conditions, hold the greatest promise for harboring life. One key focus is the study of exoplanets located in what's known as the habitable zone, or the Goldilocks zone, around their stars. This region is neither too hot nor too cold, allowing liquid water to exist, which is essential for life as we understand it. Thousands of exoplanets have already been discovered in this sweet spot, and astronomers continue to monitor their atmospheres for signs of water vapor, oxygen, and other molecules that could support life. But the search for life is not confined to distant exoplanets. The icy moons of our solar system, particularly Europa and Enceladus, remain prime candidates for the discovery of extraterrestrial life. These moons are thought to harbor vast, hidden oceans beneath their thick layers of ice, and scientists are eager to explore them further. If microbial life or even more complex organisms exist in these environments, they could provide further evidence that life may arise in diverse conditions, expanding the boundaries of what we consider to be habitable. As the search for extraterrestrial life progresses, we continue to confront deep existential questions about the nature of life, the uniqueness of Earth, and whether we are part of a larger cosmic community. Each new discovery only deepens the sense of wonder about what lies beyond our blue planet. And with every technological leap, every mission launched, and every breakthrough in understanding, we come one step closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? Astrobiologists are increasingly focusing on regions within our galaxy that are believed to be the most conducive to the emergence of life, specifically the galactic habitable zone. This zone is a particular area where the conditions for life are thought to be most favorable, taking into account several critical factors: distance from the galactic center, the chemical composition of the environment, and the density of stars. The exploration of these regions exemplifies humanity's unyielding curiosity about the possibility of life beyond Earth, driven by a fundamental hope that we are not solitary in this vast, mysterious universe. One of the key drivers of this pursuit is the remarkable discovery of extremophiles, organisms that thrive in environments previously thought to be inhospitable to life. These extraordinary creatures have been found in some of the most extreme environments on Earth, from the deepest, darkest ocean trenches to the blistering heat of geothermal springs, and even in highly acidic or radioactive surroundings. What makes extremophiles particularly fascinating is their ability to survive and even flourish under extreme conditions such as intense heat, high salinity, crushing pressure, and dangerous levels of radiation. The existence of these organisms has not only expanded our understanding of life's incredible resilience, but also revolutionized the way we think about where life could exist beyond our planet. The fact that life can thrive in such extreme conditions on Earth suggests that similar forms of life might exist elsewhere in environments long considered uninhabitable. This opens up a whole new realm of possibilities when it comes to the search for extraterrestrial life. By studying extremophiles, scientists have begun to unravel the fundamental principles that govern life's adaptability. For example, some extremophiles are capable of harnessing unique biochemical processes to convert otherwise toxic compounds into usable energy. This discovery raises intriguing questions about the potential for similar life forms to exist in other harsh environments, such as the icy moons of Jupiter and Saturn, or the challenging surface conditions of Mars. Could life survive in the subterranean oceans of Europa or Enceladus? If life can endure on Earth in such extreme conditions, it seems increasingly likely that similar ecosystems might exist elsewhere in the cosmos. Furthermore, extremophiles are integral to the emerging field of astrobiology, the study of life beyond Earth. Their discovery has helped redefine the criteria scientists use to identify potential habitable environments in space. For instance, celestial bodies with subsurface oceans, such as Europa, Ganymede, and Enceladus, which were once dismissed as unlikely candidates for harboring life, are now considered some of the most promising locations for future exploration. These environments, previously overlooked, may hold the answers to some of the most profound questions about life in the universe. Extremophiles are not only essential for shaping our understanding of potential extraterrestrial life, but they also provide critical insights into the kinds of biosignatures, chemical indicators of life, we might seek in our quest to detect alien organisms. Their diverse metabolic pathways offer vital clues about the kinds of biological markers that could be present on distant worlds. As our search for extraterrestrial life continues, these remarkable organisms remind us that life is incredibly versatile, and that the universe may be teeming with surprising forms of life waiting to be discovered. The search for life beyond Earth has also been significantly advanced by the development of mathematical frameworks such as the Drake equation. Formulated in the early 1960s by astrophysicist Frank Drake, the equation aims to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. By breaking down the complex question of extraterrestrial life into several key variables, the equation provides a scientific foundation for the ongoing search for life in the cosmos. The Drake equation multiplies factors such as the average rate of star formation in our galaxy, the fraction of stars with planets, the number of potentially habitable planets per solar system, and the likelihood of life developing on those planets. It also considers the probability of intelligent life evolving and the potential lifespan of technologically advanced civilizations capable of transmitting and receiving signals. By quantifying these variables, the equation provides a statistical framework for estimating the odds of encountering intelligent life elsewhere in the universe. What makes the Drake equation so compelling is not just the numbers it generates, but its ability to spark meaningful conversations and drive research in fields like astrobiology, astrochemistry, and planetary science. It encourages scientists to explore the uncertainties surrounding the conditions necessary for life to emerge and the factors that contribute to the development of intelligence. This ongoing research deepens our understanding of life's potential and fuels our imagination about the diversity of life that may exist beyond our planet. Though the exact outcomes of the Drake equation rely heavily on the assumptions made about each of its variables, it serves as a starting point for scientific inquiry into one of humanity's most profound questions. Are we alone in the universe? The equation continues to inspire curiosity and exploration, driving us to refine our understanding of life's conditions in the cosmos. As we venture further into space, every new discovery in astronomy and planetary science not only refines the equation, but also brings us one step closer to answering this age-old question. In recent years, the search for biosignatures, chemical signs of life, has gained momentum thanks to technological breakthroughs. Instruments like the James Webb Space Telescope, JWST, are playing a crucial role in this pursuit. With its advanced infrared capabilities, the JWST can analyze the atmospheres of exoplanets with unprecedented precision, detecting traces of complex hydrocarbons, water vapor, and even possible biological activity. This sensitivity is key to detecting the faintest signs of life, even in distant exoplanets and moons that orbit distant stars. Spectroscopy, the technique used to analyze the light emitted by distant objects, is one of the primary tools enabling these discoveries. By breaking down the light into its component wavelengths, scientists can identify the unique chemical fingerprints of various molecules in a planet's atmosphere. The integration of cutting-edge instruments into both ground-based and space-based telescopes is transforming our ability to explore distant worlds, pushing the boundaries of our search for life beyond Earth. As we continue our journey into the cosmos, these technological advancements are not only enhancing our ability to detect signs of life, they are expanding our imagination. They remind us that the universe is vast and the possibilities for discovering life, in whatever form it may take, are boundless. Moreover, recent technological strides in artificial intelligence and machine learning are dramatically altering our ability to process and interpret astronomical data. These cutting-edge algorithms are capable of sifting through vast troves of information, identifying patterns and anomalies that could suggest the presence of biosignatures, markers of potential life, far more efficiently than traditional methods. As these technologies continue to evolve, they promise to accelerate our search for life beyond Earth, enabling us to analyze exponentially more data in much shorter timeframes. This leap forward in computational power brings us closer to detecting extraterrestrial life, moving us beyond speculation to concrete findings. Simultaneously, advancements in space exploration are playing a crucial role in expanding our search for life. One of the most promising developments is the creation of small, specialized spacecraft designed for interplanetary exploration. These missions are targeting the icy moons of our solar system, such as Europa and Enceladus, which are believed to harbor subsurface oceans beneath their frozen exteriors. Utilizing advanced sensing technologies, these spacecraft are probing beneath the ice, analyzing ejected plumes of water vapor and other substances that could contain organic compounds. These compounds may offer the first definitive signs of life, or at the very least, the potential for life in these distant worlds. Together, these technological breakthroughs refine our detection methods and deepen our understanding of where and how life might arise in the vast expanse of the universe. The origin of life on Earth is one of the most profound and enduring mysteries in science. Current theories suggest that life began in a primordial soup, a complex mixture of chemicals, around 3 to 4 billion years ago. This hypothesis proposes that Earth's early environment, rich in essential organic molecules, provided the perfect conditions for the first stirrings of life. These molecules likely formed through a combination of atmospheric conditions, volcanic activity, and the energy from lightning strikes or ultraviolet radiation from the sun. This fertile ground for chemical reactions may have set the stage for the evolution of the first living organisms. One of the leading hypotheses regarding the origins of life centers on the idea of abiogenesis, the process by which simple organic compounds gradually evolved into more complex structures. For example, amino acids, the fundamental building blocks of proteins, might have assembled in the oceans, forming chains that eventually gave rise to more complex molecules, such as ribonucleic acid, RNA. RNA is capable of storing information and replicating itself, much like modern-day genes, offering a glimpse of life in its simplest form, predating the more complex DNA-based organisms that would later dominate the biosphere. This presents a fascinating model for how life could have emerged from non-living matter. In parallel, research into the extreme environments of hydrothermal vents on the ocean floor provides another compelling angle on life's origins. These underwater chimneys, which emit hot, mineral-rich water, create unique conditions that may have facilitated the first chemical reactions leading to life. The minerals released from these vents could have acted as catalysts, providing a stable and nutrient-rich environment where complex organic molecules could form and thrive. By studying the microbial life that exists in these extreme environments today, scientists hope to uncover vital clues about how life could have originated on Earth, or even how it might arise on other planets with similar conditions. While many questions remain, scientists continue to experiment in laboratories that simulate early Earth conditions, attempting to recreate the chemical pathways that could have led to the emergence of life. Each new discovery adds a crucial piece to this intricate puzzle, enhancing our understanding of how life could have developed in a universe that, at first glance, seems devoid of life, ultimately transforming our planet into the vibrant biosphere we see today. The primordial soup theory, which suggests that life began in the oceans as a mixture of simple molecules, offers a captivating glimpse into life's beginnings. This theory argues that, under the right conditions, the early oceans acted as a sort of chemical soup, where basic molecules interacted and reacted, eventually forming more complex organic compounds. The process may have unfolded over millions of years, with simple substances gradually giving rise to the intricate structures that form living organisms. A key feature of the primordial soup theory is its emphasis on the environmental factors that played a crucial role in sparking chemical reactions. Lightning, volcanic eruptions, and ultraviolet radiation could have provided the necessary energy to drive the formation of amino acids, nucleotides, and other essential building blocks. This process likely took place in a natural laboratory, where the raw materials of life slowly combined and evolved into more complex forms. One of the most famous experiments supporting this idea is the Miller-Urey experiment, conducted in the 1950s by scientists Stanley Miller and Harold Urey. They recreated the conditions of early Earth by mixing water, methane, ammonia, and hydrogen in a sealed environment and then introducing electrical sparks to simulate lightning. Remarkably, this experiment resulted in the formation of amino acids, the very building blocks of proteins. This groundbreaking discovery lent significant credence to the primordial soup theory, providing experimental evidence that organic molecules could form under conditions similar to those of early Earth. In the broader context of life's origins, the primordial soup theory remains a cornerstone of scientific inquiry, inspiring further exploration and research. While contemporary theories, such as those focusing on hydrothermal vents or extraterrestrial origins, have expanded our understanding of how life could arise, the primordial soup theory continues to captivate the imagination. It represents a compelling starting point for understanding the remarkable journey from simple molecules to the diverse, thriving ecosystems that populate our planet today. Each new discovery, from the detection of organic compounds on distant moons to the simulation of early Earth conditions in the lab, adds another layer of complexity to this ongoing tale. As we continue to explore the origins of life, both on our planet and beyond, we are reminded of the profound mystery that surrounds our existence and the vast, uncharted potential for life in the universe. Deep beneath the ocean's surface, in the darkest, most hostile regions of our planet, there exists a network of hydrothermal vents that have captivated scientists for decades. These natural phenomena are not just curious geological formations. They are at the heart of some of the most profound questions about the origins of life on Earth. Here, in the utter absence of sunlight and in extreme conditions of pressure and temperature, life thrives in ways that challenge everything we once believed about how life could exist. Hydrothermal vents are openings in the Earth's crust that release superheated mineral-rich water from deep within the planet. Unlike any ecosystem we've encountered on the surface, these vents support a wide array of life forms, some of which are completely alien to our understanding. What makes these ecosystems so extraordinary is that they are powered not by the sun, but by a process known as chemosynthesis. In this process, microbes use chemicals like hydrogen sulfide released from the vents as an energy source. These microbes, the foundation of this unique ecosystem, do not rely on photosynthesis, the process most life on Earth depends on. Instead, they harness the energy in the chemicals present in the vent water to survive, thriving in an environment previously considered too harsh for life to exist. This discovery has had profound implications for how we think about the potential for life beyond Earth. If life can survive in such extreme conditions, it's possible that it could have originated in similar environments, possibly on other planets or moons. It forces us to reconsider the conventional idea that sunlight is a necessary ingredient for life. The vents, in their isolation from sunlight, serve as proof that life could thrive in environments radically different from our own. This insight not only reshapes our understanding of life on Earth, but also opens new avenues of thought about life in the vastness of space. One particularly intriguing theory suggests that life on Earth may have started in environments like these, alkaline hydrothermal vents. In these vents, hot fluids from the Earth's interior mix with cold ocean water, creating the perfect conditions for chemical reactions. These reactions could have been the very catalysts that formed simple organic molecules, the building blocks of life. Over time, as these molecules accumulated and reacted further, they may have eventually formed more complex structures, paving the way for the first true living organisms. This theory, which places the origins of life in the depths of the ocean rather than in shallow tidal pools, challenges long-standing assumptions and brings fresh excitement to the field of evolutionary biology. The implications of this discovery extend beyond Earth. Some of the most promising locations for finding extraterrestrial life are moons like Europa and Enceladus, both of which exhibit signs of hydrothermal activity beneath their icy surfaces. These environments could potentially harbor the same kinds of chemical processes that gave rise to life on Earth. By studying hydrothermal vents on our own planet, scientists are not only unraveling the mysteries of our past, but also gaining insights into the potential for life elsewhere in the universe. But the search for life's origins doesn't end with the study of hydrothermal vents. Meteorites, those celestial travelers that have been hurtling through space for billions of years, carry with them the potential clues to the very beginnings of life. These ancient rocks, remnants from the early solar system, contain a treasure trove of organic molecules, including amino acids, vital building blocks for life. Their journey through the vacuum of space, their eventual landing on Earth, and their contents spark intense curiosity among scientists about whether the ingredients for life might have been distributed across the cosmos long before life arose on our planet. Meteorites are key to one of the most fascinating theories of life's origins, panspermia. This theory suggests that life, or at least the essential components necessary for life, could have been transported throughout the universe via comets, asteroids, and other cosmic debris. If these molecules could survive the harsh conditions of space, extreme cold, radiation, and the vacuum, then it is conceivable that Earth was seeded with the necessary ingredients for life from elsewhere in the universe. Certain types of meteorites, like carbonaceous chondrites, have been of particular interest to researchers due to their rich content of organic molecules. Studies have even shown that these meteorites can produce amino acids under conditions similar to those on early Earth, suggesting that the very building blocks of life may have originated far beyond the confines of our planet. In this light, meteorites are no longer just space debris. They are cosmic time capsules, holding fragments of a distant past that may refer to one of humanity's most profound questions. How did life begin? By studying the contents of these ancient space rocks, scientists are piecing together a story that links Earth to the far reaches of the cosmos. These celestial objects hold the potential not only to explain our own origins, but also to reveal whether life might exist elsewhere in the universe. Throughout Earth's history, there have been moments of profound upheaval, catastrophic extinction events that reshape the course of life on this planet. These events, triggered by massive volcanic eruptions, asteroid impacts, and drastic climate changes, have led to the loss of entire ecosystems. However, they have also set the stage for dramatic periods of evolution, where life found new pathways and opportunities to flourish. One of the most significant extinction events in Earth's history was the Permian-Triassic extinction, often referred to as the Great Dying. Occurring around 252 million years ago, this event wiped out nearly 90% of marine species and 75% of terrestrial species. In the aftermath, the planet was left with vast ecological openings and new evolutionary pathways emerged. This cataclysm set the stage for the rise of the dinosaurs and later the mammals, illustrating how extinction events can clear the way for entirely new forms of life to evolve and fill ecological niches that were once occupied by dominant species. Similarly, the Cretaceous-Paleogene extinction, which occurred about 66 million years ago, famously led to the demise of the dinosaurs. The event also had a profound impact on mammals, which, once overshadowed by the reign of dinosaurs, began to diversify rapidly in the wake of their extinction. This led to the rise of new species, including primates, and eventually to the emergence of human beings. The shift from dinosaur-dominated ecosystems to mammal-dominated ones is a striking example of how extinction can serve as a catalyst for evolutionary creativity. These events underscore a fascinating principle in evolutionary biology. Sometimes the removal of dominant species allows for the rapid evolution of other organisms that can adapt to the newly available environments. Extinction may seem like a destructive force, but in the long run, it has often been a driving force behind the development of new forms of life. It is a reminder of the resilience of life on Earth and the incredible capacity for organisms to adapt, evolve, and thrive in the face of overwhelming change. The theory of evolution, first articulated by Charles Darwin, provides a powerful framework for understanding how the diverse forms of life we see today came to be. From the simplest microbes in the depths of the ocean to the complex ecosystems that fill our planet, evolution has been the guiding force behind the development of life on Earth. As we continue to study the origins of life, from hydrothermal vents to meteorites, we uncover deeper layers of understanding about the delicate, interconnected web of life that has shaped our planet, and perhaps, by extension, the entire universe. The theory of evolution proposes that all living organisms share a common ancestor, and over vast stretches of time, species have transformed and diversified through a fundamental process known as natural selection. This process occurs when organisms possessing traits that are better suited to their environment have a higher chance of surviving and reproducing. Over many generations, these advantageous traits become more prevalent within a population, gradually leading to the emergence of new species. The slow, methodical process of evolution unfolds across epochs, revealing the deep complexity behind the staggering biodiversity we observe in ecosystems across the globe today. At the heart of evolution lies genetic variation, the foundation for adaptation. This variation arises from mutations, gene flow, and sexual reproduction, which create a range of traits within a population. Mutations, which are random changes in an organism's DNA, can introduce new traits, some of which may offer survival advantages. Similarly, sexual reproduction contributes to genetic diversity, ensuring that offspring inherit a unique combination of genes from both parents. Gene flow, the exchange of genetic material between populations, further enriches genetic diversity, providing a broader spectrum of traits that might be beneficial in a changing environment. As environments shift, whether through climate changes, fluctuations in food supply, or the complex predator-prey relationships that characterize natural ecosystems, the organisms most adept at navigating these pressures tend to thrive. But this survival is not immediate. It unfolds over millions of years as subtle changes accumulate, slowly reshaping the landscape of life. In addition to these genetic mechanisms, the fossil record offers an invaluable window into the past. Fossils serve as physical remnants of ancient life forms, offering a chronological account of how species have evolved over time. Through the study of fossils, scientists can trace morphological changes in the skeletal structures of organisms, shedding light on the connections between species, and highlighting how traits have evolved over millennia. For instance, the discovery of Archaeopteryx, a transitional fossil, has provided evidence of the evolutionary link between reptiles and birds, showing how specific traits, such as feathers, gradually evolved. This fossil not only connects two distinct groups of animals, but also highlights the gradual, often incremental nature of evolutionary change. Similarly, advancements in genetic research, particularly DNA sequencing, have allowed scientists to probe deeper into the connections between different species. By comparing genetic codes, researchers can determine how closely related organisms are and reconstruct the paths that have led to their current forms. The theory of evolution, bolstered by both fossil evidence and genetic analysis, reveals the shared ancestry of all life. It reinforces the idea that all organisms are interconnected through a vast, intricate web of evolutionary pathways. This interconnectedness underscores the dynamic and ongoing nature of adaptation and change in the living world, reminding us that life on Earth is constantly evolving, reshaping itself in response to the forces of natural selection. Natural selection is the driving force behind much of this adaptation. First proposed by Charles Darwin, this principle states that individuals with traits better suited to their environment are more likely to survive and reproduce. Over time, the favorable traits become more common in the population, leading to the emergence of new adaptations, or in some cases, entirely new species. Natural selection acts on genetic variation, which provides the raw material for evolutionary change. However, natural selection is just one piece of the puzzle. Mutation, the random alteration of genetic material, introduces new traits that can sometimes offer a survival advantage. These mutations may be small or large, and while many are neutral or harmful, some confer significant benefits in particular environments. Genetic drift, the random fluctuation of gene frequencies in small populations, also plays a role in shaping the evolution of species, contributing to the diversity of life in unexpected ways. Together, these mechanisms, mutation, genetic drift, and natural selection, interact in complex ways, producing the diversity of life forms we see today. Evolution is not a simple linear process, but a dynamic, multifaceted journey shaped by an array of factors, including random events and selective pressures. Whether through the gradual accumulation of small changes or through more drastic shifts triggered by environmental pressures, adaptation is a continuous process, revealing the resilience and adaptability of life on Earth. Mass extinctions, the catastrophic events that lead to the rapid disappearance of a large number of species, represent dramatic turning points in evolutionary history. 5 major mass extinctions have occurred throughout Earth's history, each of them reshaping ecosystems in profound ways. These events not only wiped out dominant life forms, but also created ecological niches that survivors could occupy. In turn, these survivors often underwent a process known as adaptive radiation, rapidly evolving to fill the ecological roles left vacant by extinct species. One of the most famous examples of adaptive radiation occurred after the extinction of the dinosaurs around 66 million years ago. With the dinosaurs gone, mammals, which had previously been small and relatively inconspicuous, began to diversify rapidly. They evolved into a variety of forms, including the ancestors of humans. This massive extinction event opened the door for entirely new evolutionary paths, giving rise to a completely different ecological landscape. Mass extinctions also bring about new survival strategies. In the aftermath of such events, the organisms that survive often develop enhanced adaptability, learning to cope with new environmental conditions. This flexibility allows for the creation of more complex and varied ecosystems, as surviving species develop new relationships with one another and their surroundings. The interplay of survival and adaptation in the wake of mass extinctions underscores the resilience of life, illustrating that even in the face of destruction, evolution continues to find new ways to thrive. Humans, with our intricate cognitive, physiological, and social adaptations, stand out as one of the most remarkable products of evolutionary processes. One of the most striking aspects of our evolution is the size and structure of our brain. Unlike most animals, humans possess a brain that is not only larger relative to body size, but also highly organized for complex thinking, problem solving, and abstract reasoning. This unique cognitive ability has enabled us to develop language, create art, and engage in complex social and technological innovations, capabilities that separate us from other species. Another key human adaptation is our ability to walk upright, bipedalism. This shift from quadrupedalism to bipedalism freed our hands for tool use and manipulation, a pivotal factor in our evolutionary success. The ability to stand and walk on two legs not only increased our mobility, but also expanded our field of vision, allowing us to better spot potential dangers and resources. This newfound efficiency in movement, combined with dexterous hands, enabled humans to thrive in diverse environments, giving us a unique edge in the evolutionary race. Yet, perhaps one of the most defining human traits is our capacity for social cooperation. Unlike most animals, humans have developed intricate social structures that allow us to work together in large groups, share resources, and care for each other beyond familial ties. This ability to form cooperative relationships has enabled humans to build complex societies and civilizations, which have, in turn, propelled advances in science, technology, culture, and social welfare. This intricate web of adaptations, our brain capacity, upright posture, and social bonds, has made humanity not only a remarkable product of evolution, but also a testament to the power of adaptation. As humans continue to evolve, these traits will undoubtedly shape our future just as they have shaped our past, guiding us into the next phase of our species' evolutionary journey. Human adaptability to a wide range of environments is one of the most striking aspects of our species, a testament to the resilience that defines us. While most species are confined to specific habitats, humans have demonstrated an unparalleled ability to not only survive, but thrive in a vast array of environments. From the harsh, frozen expanse of the Arctic tundra to the lush, rain-drenched jungles of the tropics, we have shown that no corner of the Earth is beyond our reach. This remarkable ability stems from our innovative use of technology, as well as our capacity to modify and transform our surroundings. Once inhospitable places have been reshaped to accommodate our needs, allowing us to live and flourish in areas once thought impossible to inhabit. This unique combination of cognitive, physiological, social, and environmental adaptations is what sets humans apart from other species. We are not merely survivors, but agents of change, constantly shaping the world around us to fit our needs. In doing so, we are not only responding to the environment, but actively influencing it. Our ability to manipulate both our physical and social environments has become a defining characteristic of our species. At the heart of this process of adaptation lies the concept of genetic mutations, the raw material for evolution. Genetic mutations are changes in the DNA sequence, which can occur for a variety of reasons. Environmental factors, errors during DNA replication, or even random chance can cause these mutations. These changes may lead to alterations in an organism's traits, potentially making it better suited to its environment. If a mutation provides a survival advantage, it can enhance the organism's chances of reproducing, passing these advantageous traits down to future generations. This process is a fundamental driver of evolutionary change. Mutations come in many forms, from the smallest point mutations, which involve a change in a single nucleotide, to more significant alterations, such as deletions or duplications of genetic material. Some mutations may have little to no effect, while others can drastically affect an organism's ability to function. However, it is the beneficial mutations that persist, as they are favored by natural selection. Organisms with advantageous traits are more likely to survive and reproduce, passing these traits on to their offspring, gradually shaping the genetic makeup of the population over time. This dynamic interplay between genetic mutations and natural selection forms the cornerstone of evolutionary theory. Over generations, these small, cumulative changes can lead to the emergence of new species, or the adaptation of existing species to their changing environments. The evolution of life on Earth is a slow, ongoing process that is deeply influenced by both genetic variation and the pressures exerted by the environment. Throughout Earth's history, this process has given rise to some of the most fascinating adaptations. For example, the long necks of giraffes are thought to have evolved as a response to competition for food in trees. This adaptation allowed them to reach higher branches, giving them access to a food source that other herbivores could not reach. Such adaptations are the result of countless generations of genetic mutations, acting in concert with environmental pressures, creating the diverse array of species we see today. One of the most profound aspects of life on Earth is its incredible biodiversity. Biodiversity refers to the vast variety of life found in different ecosystems, from the smallest microorganisms to the largest mammals, and the wide range of plants that populate our planet. This rich tapestry of life is essential to the health and resilience of ecosystems, enabling them to withstand environmental stresses and adapt to changing conditions. Biodiversity contributes significantly to the stability and productivity of ecosystems. Different species perform various roles within an ecosystem, ensuring that the system functions smoothly. For example, many species perform similar tasks, such as pollination, nutrient cycling, and pest control. This redundancy within ecosystems provides a safeguard against disturbances, such as climate change, disease, or human interference. If one species declines due to habitat loss or other factors, other species can often step in to fulfill the same role, thus maintaining the balance of the ecosystem. Moreover, ecosystems with greater biodiversity are generally more productive. Different species use resources like sunlight, water, and nutrients in distinct ways, which can lead to more efficient use of these resources. This results in higher rates of photosynthesis and nutrient uptake, ultimately contributing to greater biomass and overall ecosystem productivity. Healthy, biodiverse ecosystems provide essential services such as clean air, water, soil regeneration, and carbon sequestration, critical functions for human survival and for mitigating the effects of climate change. Biodiversity also strengthens the adaptive capacity of ecosystems. Species with diverse genetic backgrounds are better equipped to withstand environmental changes, whether due to disease, climate shifts, or other stresses. This genetic diversity acts as a safety net, ensuring that some members of a population can thrive, even when conditions become challenging. The more genetically diverse a population, the more likely it is to have individuals capable of surviving and adapting to new threats. Protecting biodiversity is not just about conserving rare or iconic species. It is about safeguarding the intricate web of life that supports all living organisms, including humans. The preservation of biodiversity is essential for maintaining healthy ecosystems that can continue to provide the services we rely on for our survival. As the planet's ecosystems face growing threats, preserving biodiversity becomes more crucial than ever. Unfortunately, biodiversity today faces an unprecedented array of challenges. One of the most significant threats is habitat loss. As human populations expand, natural habitats are increasingly transformed into urban areas, agricultural fields, and industrial sites. This loss of habitat not only endangers the species that rely on these environments, but also disrupts entire ecosystems, threatening the delicate balance that sustains life. Climate change is another major factor driving biodiversity loss. Rising global temperatures are altering weather patterns, shifting habitats, and forcing species to adapt, migrate, or face extinction. Ocean acidification, a consequence of increased carbon dioxide absorption, is particularly harmful to marine life, especially coral reefs, which support a wide range of organisms. As the climate continues to change, many species struggle to survive, leading to a decline in biodiversity and the disruption of ecosystems. Invasive species present yet another formidable threat to biodiversity. These organisms, often introduced to new environments unintentionally, can outcompete native species for resources, disrupt food chains, introduce diseases, and alter ecosystems. The result is a decline or extinction of native species, further diminishing biodiversity and altering the landscape in profound ways. As we confront these threats, it becomes clear that preserving biodiversity is not just about protecting individual species. It is about preserving the intricate systems that sustain life on Earth. The health of our planet and ultimately our own survival depends on the richness and resilience of the ecosystems that we share with countless other species. Pollution, especially from plastics and chemicals, presents one of the most significant environmental threats of our time. Across the globe, pollutants contaminate essential natural resources, water, soil, and air, directly impacting the health of countless species, including humans. These harmful substances don't just threaten wildlife, they jeopardize entire ecosystems. The cumulative effects of such pollution are contributing to an alarming decline in global biodiversity, making the need for preservation efforts more urgent than ever. If we are to sustain the rich variety of life that defines our planet, swift action is essential. One powerful way to shape current conservation efforts is by studying species that have gone extinct. These extinct species offer a fascinating window into our planet's past and the complex dynamics of its ecosystems. Each extinction story carries important lessons about the underlying factors that cause the species' demise, whether through habitat destruction, climate change, or the pressures of interspecies competition. Understanding these historical contexts allows scientists to pinpoint the vulnerabilities of species that are currently endangered, providing valuable insights for creating more effective preservation strategies. For example, the extinction of a species often reveals how an ecosystem adjusts to the loss of a key organism. Consider the role of long-gone predators in an ecosystem. Their absence can lead to significant imbalances, such as an overpopulation of prey species that exhausts vital resources. By examining these shifts, conservationists gain essential knowledge about the interdependent relationships within ecosystems and how to restore balance by protecting or reintroducing similar species when possible. This approach underscores the importance of each species within the delicate web of life. Every organism plays a specific role, and its absence can reverberate throughout the ecosystem. Additionally, the genetic makeup of extinct species can provide valuable information about traits that may benefit their modern counterparts. By studying the genetic legacy of extinct species, scientists can uncover traits that helped species survive challenges in the past, from disease resistance to climate adaptation. These insights enable the development of targeted breeding programs for endangered species, bolstering their resilience against contemporary threats such as disease outbreaks and climate change. In this way, the study of extinct species is not only a way to honor the past, but a resource for protecting the future. The lessons learned from the extinction of species act as both a cautionary tale and a critical resource. By applying this knowledge, we can better understand our role within the ecosystem and the profound responsibility we bear in protecting biodiversity. Conservation is not just about preserving the species we still have, but also about learning from the past to secure a thriving future for all life on Earth. One of the most vital aspects of a species' ability to survive and adapt is its genetic diversity. This diversity refers to the variety of genetic traits within a population, and it plays a fundamental role in a species' ability to withstand environmental challenges. Populations with low genetic diversity are at a higher risk of being wiped out by diseases, environmental changes, or other pressures that threaten their survival. For example, imagine a population of plants in a region experiencing climate shifts. If every individual plant shares the same genetic makeup, all may respond similarly to changes in temperature or water availability, leaving them vulnerable to extinction. However, when genetic diversity is present, some plants may possess traits that allow them to thrive under new conditions, such as drought resistance or an ability to endure higher temperatures. This genetic variety increases the likelihood that at least some individuals will survive and reproduce, ensuring the continuation of the species. The same principle applies to wildlife populations. Genetic diversity enhances resilience, allowing animals to develop new behaviors or exploit alternative resources in response to threats like habitat destruction or pollution. A population with a diverse genetic pool acts like a well-stocked toolbox, offering a variety of strategies to cope with the challenges of an ever-changing world. It is not just the survival of individual species that depends on this diversity, but also the stability of entire ecosystems. Ecosystems are intricate networks of interdependent species where each organism plays a specific role. The health of these systems relies on the balanced interactions between species, which can be mutually beneficial, as in the case of pollinators and plants, or more competitive, such as predator-prey dynamics. In a mutually beneficial relationship, such as between flowering plants and their pollinators, both parties thrive. The plants rely on insects or birds to spread their pollen, while the pollinators depend on the nectar for sustenance. If one part of this relationship is disrupted, it can trigger a ripple effect throughout the ecosystem, endangering not only the plants that depend on pollination, but also the animals that rely on those plants for food. Predator-prey relationships further highlight the delicate balance within ecosystems. Predators help regulate prey populations, preventing overgrazing or overpopulation. Without predators, certain prey species could proliferate uncontrollably, leading to resource depletion and possibly the collapse of the ecosystem. This natural regulation supports the stability of the food chain, ensuring that each species within the ecosystem remains viable and that resources are used sustainably. Ultimately, the loss of any species, whether predator or prey, plant or animal, can have far-reaching consequences. The interconnectedness of all living things is what sustains the complex web of life on Earth. Each species, no matter how small or seemingly insignificant, plays a crucial role in maintaining the balance and health of the ecosystem. This interdependence is a reminder that conservation efforts must be comprehensive, protecting not just the endangered species we can see, but the invisible threads that tie them all together. As we face mounting environmental challenges, it becomes clear that preserving biodiversity is not a luxury, but an urgent necessity for the survival of our planet and all its inhabitants. The intricate relationships that sustain ecosystems extend far beyond the immediate interactions we typically observe in food webs. Decomposers, such as fungi and bacteria, play a crucial role in breaking down dead organisms, turning organic material into vital nutrients. This recycling process is essential for maintaining the health of the soil and, by extension, the entire ecosystem. It creates a cycle that ensures new plant growth can take root and flourish, feeding the entire web of life. Without these decomposers, ecosystems would fail to regenerate, resulting in a collapse of the intricate balance that allows life to persist. At the heart of this process is the concept of interconnectedness. Every organism, whether a small microbe or a large predator, plays a unique role in maintaining the ecosystem's stability. By examining the ways in which different species interact, we come to understand the profound importance of these relationships. The entire structure of life, both plant and animal, is inextricably linked, and understanding these connections is key to preserving the delicate balance of our ecosystems. As we delve deeper into this knowledge, we uncover ways to protect these fragile systems that are vital to the survival of countless species, including our own. Beyond ecosystems, the study of intelligence in animals has also seen a dramatic shift in recent years. Traditionally, intelligence was considered a trait exclusive to humans. However, a growing body of research has revealed that a wide range of species exhibit cognitive abilities that rival and, in some cases, surpass those of humans. Scientists now define intelligence as the ability to learn, solve problems, adapt to new situations, and understand complex ideas. This definition extends far beyond human beings, encompassing a vast spectrum of species with unique and diverse ways of demonstrating intelligence. One fascinating example of this is the dolphin, whose intelligence is often evaluated through its social behaviors and communication skills. Dolphins display complex social structures, and their ability to communicate using a series of clicks and whistles demonstrates not only a deep understanding of their environment, but also an extraordinary level of cognitive sophistication. Their communication skills also extend to coordinated hunting strategies, where they use sound signals to alert one another and increase their chances of success. Crows, on the other hand, showcase their intelligence through their remarkable problem-solving abilities. These birds have been observed using tools in innovative ways, such as crafting sticks and leaves to extract insects from tree bark. This tool use indicates not only an understanding of cause and effect, but also a level of foresight and innovation. The New Caledonian crow, in particular, has become a symbol of avian intelligence, known for its exceptional skill in crafting tools from materials found in its environment. To study these various forms of intelligence, scientists use a variety of methods. Behavioral tests are often employed to assess cognitive abilities such as memory, reasoning, and social interaction. Tasks like navigating mazes or solving puzzles challenge animals to think critically, providing insights into their problem-solving processes. These tests are designed to go beyond measuring the outcomes of tasks. They also help scientists understand how animals approach problems, revealing the intricate mental processes behind their actions. Furthermore, observational studies of social intelligence are increasingly important in the study of animal cognition. Many animals, such as primates and certain birds, exhibit complex social behaviors that require a nuanced understanding of relationships, hierarchies, and cooperation. By observing these social interactions, scientists can gain insights into the dynamics of group behavior and the role of intelligence in maintaining harmony within these groups. Evidence of empathy, cooperation, and even deception in animals such as elephants and dogs highlights the complex nature of animal intelligence, offering new perspectives on how these traits have evolved and how they contribute to survival in the wild. As scientists continue to explore animal cognition, they are challenged to rethink our traditional definitions of intelligence. Rather than being a fixed human-centric trait, intelligence is now seen as a spectrum, with each species evolving unique strategies and skills suited to its specific environment. This ongoing exploration not only deepens our understanding of the animal kingdom, but also sparks awe at the diverse forms of intelligence that exist in nature. In the realm of animal cognition, one particularly fascinating area of study involves the use of tools. Many animals, from chimpanzees to sea otters, have been observed using objects in their environment to help them solve problems, such as fishing or opening shellfish. This behavior suggests not only an understanding of cause and effect, but also an awareness of future outcomes. In fact, tool use in animals points to a level of cognitive sophistication that was once thought to be exclusive to humans. The New Caledonian crow, in particular, has been shown to craft intricate tools to extract food, demonstrating a high degree of innovation and problem-solving ability. Communication, too, plays a key role in animal cognition. Dolphins, known for their social and cooperative behavior, use a complex system of clicks, whistles, and body movements to communicate with one another. This communication is essential for coordinating group activities, including hunting and navigation. Similarly, primates and certain bird species also exhibit advanced communication systems that are integral to their social structures. The study of these communication systems provides valuable insights into the cognitive abilities of non-human animals and helps us better understand the evolution of social intelligence. Moreover, behavioral ecology has revealed that many animals possess traits such as empathy, cooperation, and even deception. These behaviors are not merely survival tactics. They also point to the emotional and social depth of animal intelligence. For instance, elephants are known to exhibit empathy toward other members of their herd, offering comfort and assistance when needed. Dogs, too, demonstrate cooperation and even deceive their human companions in playful ways, revealing the complexity of their cognitive and emotional lives. As we continue to study animal intelligence, we are forced to expand our understanding of what it means to be intelligent. Intelligence is not a monolithic concept. It is diverse and multifaceted, shaped by each species' unique ecological and social challenges. The exploration of animal cognition invites us to reconsider our preconceived notions about intelligence and appreciate the many different ways it can manifest across the natural world. Consciousness, perhaps the most profound and elusive aspect of the human experience, has long intrigued scientists, philosophers, and neurologists alike. From a scientific perspective, consciousness is often seen as the result of complex neural processes within the brain, allowing us to be aware of ourselves, our surroundings, and our thoughts. While significant progress has been made in identifying specific brain regions associated with conscious experiences, a universal definition of consciousness remains elusive. Cognitive neuroscience, a field that examines the relationship between brain activity and conscious thought, has made important strides in understanding this phenomenon. Advanced imaging techniques, such as functional magnetic resonance imaging, fMRI, allow scientists to observe brain activity in real time, offering valuable insights into the neural correlates of consciousness. For instance, studies have shown that areas like the prefrontal cortex are activated during self-reflection, suggesting that this region plays a key role in our awareness of self and others. While we have made great strides in mapping the neural processes that underpin consciousness, the full nature of this phenomenon remains one of science's greatest mysteries. However, as we continue to explore these complex processes, we gain deeper insights not only into human cognition, but also into the broader nature of consciousness across all forms of life. Consciousness, the profound experience that allows us to be aware of our surroundings, emotions, and thoughts, has captivated scientists and philosophers alike for centuries. While the biological underpinnings of consciousness are being actively investigated, the emergence of subjective experiences from neural processes remains one of the greatest mysteries. Various theories aim to offer insights into this phenomenon, each offering unique perspectives on how consciousness might arise from the complex web of neural activity. Among these, the Integrated Information Theory, IIT, posits that consciousness emerges from the synthesis of information across various neural networks. This theory suggests that consciousness reflects the degree to which a system can integrate information, creating a unified, holistic experience. It frames consciousness as a process of information exchange, where each component contributes to the larger picture, much like individual puzzle pieces coming together to form a coherent image. In contrast, the Global Workspace Theory, GWT, presents a different angle. According to GWT, consciousness acts as a platform that allows information to be made available to various cognitive processes. It is akin to a stage where different neural activities are broadcasted to the rest of the brain, enabling us to act, make decisions, and respond to the environment. These theories illustrate the diverse viewpoints on how consciousness could arise from biological systems, each focusing on different aspects of neural activity and integration. Despite these promising theories, the core question remains: how do subjective experiences arise from neural activity? This question transcends neuroscience, touching on deep philosophical issues that challenge our understanding of reality, self-identity, and existence. As research advances, the journey to unravel the nature of consciousness becomes a multifaceted endeavor, blending science with profound philosophical inquiry. It is a quest that will continue to challenge our perceptions of what it means to be aware, to experience, and to exist. Neuroscientists, armed with advanced technologies and innovative methods, are dedicated to uncovering the complexities of the brain. One of the primary tools in this exploration is neuroimaging, particularly magnetic resonance imaging, MRI. MRI provides researchers with a detailed look at the brain's structure, revealing the intricate networks that shape our thoughts, behaviors, and experiences. Functional MRI, fMRI, goes even further by tracking blood flow in real time, allowing scientists to observe which brain regions are activated during different tasks and mental states. This non-invasive technique is a crucial tool for understanding how the brain processes information and reacts to external stimuli. Beyond neuroimaging, electrophysiology plays a pivotal role in understanding brain function. By using electrodes to measure the electrical activity of neurons, scientists can observe how neurons communicate with one another. This technique reveals the dynamic processes that underpin cognitive functions such as memory, learning, and emotional experiences. These electrical impulses, though invisible to the naked eye, offer a direct window into the brain's internal workings, helping researchers decipher the pathways that shape our thoughts and behaviors. Behavioral studies provide another key avenue for exploring the brain's complexity. By observing how individuals respond to different stimuli or situations, researchers can link specific cognitive processes to neural mechanisms. These experiments, ranging from simple memory tasks to complex decision-making scenarios, help scientists understand how various brain functions manifest in behavior. Behavioral studies are particularly useful for identifying disruptions in neural activity, offering insights into conditions such as anxiety, depression, and cognitive disorders. Furthermore, advances in genetic and molecular biology are contributing to our understanding of the brain's inner workings. Genetic research helps scientists identify how variations in our DNA influence cognitive abilities and predispositions to neurological disorders. The development of optogenetics, a technique that uses light to control specific neurons, has opened new frontiers in neuroscience. By selectively activating or deactivating neurons, researchers can gain unprecedented insights into how different regions of the brain interact and contribute to complex mental processes. Together, these various research techniques are advancing our knowledge of the brain's structure and function. With each breakthrough, neuroscientists are uncovering new aspects of the brain's remarkable ability to adapt, heal, and reorganize itself. This ongoing research is not only reshaping our understanding of how the brain works, but also providing valuable insights into the nature of consciousness itself. Despite these advances, the question of consciousness remains one of the most profound challenges in both science and philosophy. Consciousness, at its core, is the state of being aware of one's thoughts, feelings, and surroundings. Yet, despite significant progress in the fields of neuroscience, psychology, and cognitive science, we still struggle to answer the fundamental question: what is consciousness, and how does it arise? The subjectivity of conscious experience is one of the main obstacles in studying consciousness. Each individual's experience is shaped by their personal thoughts, emotions, and perceptions, making it difficult to quantify or measure. Unlike physical phenomena, which can be observed and tested objectively, consciousness is inherently personal and elusive. This subjectivity challenges researchers to find indirect ways to study it, often relying on behavioral observations and brain imaging to infer the presence and nature of conscious experience. Adding to the complexity is what philosopher David Chalmers calls the hard problem of consciousness. This term refers to the difficulty in understanding how physical processes in the brain give rise to subjective experiences, the vivid inner life that we each experience. While scientists have made significant progress in mapping brain activity and relating it to behavior, the leap from neural processes to subjective experience remains a profound mystery. This raises fundamental questions about the nature of consciousness. Is it merely a byproduct of brain activity, or is it something more profound, a fundamental feature of the universe yet to be fully understood? Exploring altered states of consciousness, whether through meditation, psychedelics, or trauma, adds another layer of complexity to the issue. These states reveal the incredible flexibility and malleability of consciousness, offering glimpses into how it can be shaped, altered, and redefined. Each of these states offers valuable insights into the workings of consciousness, yet they also highlight how much more we need to learn. Ultimately, the pursuit of understanding consciousness is not just an academic or scientific endeavor. It is a quest that ties into fundamental questions about the nature of reality itself. What is the essence of being? How do we come to experience the world as we do? The answers to these questions are bound to reshape our understanding of what it means to be alive and aware. Meanwhile, in the field of astronomy, groundbreaking advancements in telescope technology are transforming our understanding of the universe. The James Webb Space Telescope, which began its scientific observations in July 2022, has enabled astronomers to peer deeper into space than ever before. With its ability to observe infrared light, Webb can capture images of galaxies and stars from the earliest moments of the universe, providing insights into their formation and evolution. This technological leap is opening new doors to understanding the cosmos, potentially shedding light on the origins of galaxies and the nature of the universe itself. Ground-based telescopes are also making significant strides. Equipped with adaptive optics, these telescopes can correct for atmospheric distortions, offering a clearer and more detailed view of celestial objects. The extremely large telescope, currently under construction, is set to be the largest optical telescope in the world, with an aperture of 39 meters. This immense capability will allow scientists to study exoplanets in unprecedented detail, probing their atmospheres and searching for signs of habitability. Additionally, the telescope will explore the mysteries of dark matter and dark energy, two of the universe's most elusive and enigmatic phenomena. Together, these technological advancements in both neuroscience and astronomy represent a new frontier in our quest to understand both the brain and the universe. As we continue to unravel the mysteries of consciousness and explore the vast reaches of space, we are reminded of the complexity, wonder, and endless potential for discovery that exists within both the mind and the cosmos. Radio telescope technology has undergone a revolutionary transformation over recent years, with projects like the Square Kilometer Array poised to redefine our capacity for detecting faint radio signals from distant, enigmatic cosmic phenomena. The scope of this advancement is staggering. With unprecedented sensitivity, this project will allow astronomers to peer deeper into the cosmos than ever before, unlocking the secrets of the universe's infancy. As this technology evolves, it will enable us to study the early universe in unparalleled detail, revealing not just galaxies, but the intricate structures that form the very fabric of the cosmos itself. The enhanced capabilities of these radio telescopes will open new windows of exploration. By mapping the universe in greater detail, we will gain insights into the dynamics of galaxy formation, the mysterious forces shaping cosmic expansion, and the birth of stellar systems. These revelations will not only change how we view our place in the universe, but will also inspire an ever-deepening curiosity about the infinite possibilities that lie beyond the stars. Each breakthrough in telescope technology pushes the frontier of human knowledge at an exponential rate. As new discoveries unfold, the universe unveils itself in ways previously unimaginable, showing us that the potential for scientific discovery is boundless. These innovations remind us that we are at the threshold of a new era in cosmic understanding, where the questions we've asked for centuries are finally within our grasp, and new questions emerge with every answer we uncover. Space missions, too, have fundamentally altered our comprehension of the solar system, revealing secrets that were once locked away beyond the reach of Earth-bound observations. Before these missions, our knowledge was largely based on telescopic observations and theoretical predictions. But with spacecraft now venturing directly to planets, moons, and distant celestial bodies, a wealth of new data has become available, leading to unexpected discoveries that challenge and expand our understanding of the solar system. Consider the Voyager missions, launched in the late 1970s. Initially designed for flybys of Jupiter and Saturn, Voyager 1 and 2 went on to reveal far more than scientists had ever anticipated. These spacecraft captured stunning images of the gas giants and their moons, revealing the dynamic nature of our planetary neighbors. They uncovered active volcanoes on Io, detailed the intricate ring system of Saturn, and exposed the harsh but intriguing surface of Titan, Saturn's largest moon. The data sent back by the Voyagers has reshaped our understanding of planetary atmospheres, tectonics, and even the potential for life in the outer reaches of the solar system. Closer to home, missions like the Mars rovers have completely transformed our understanding of the red planet. Rovers such as Curiosity and Perseverance have ventured across Mars's barren surface, conducting groundbreaking experiments and searching for signs of ancient life. Their discoveries have painted a picture of Mars as a planet that once hosted liquid water and a climate that may have been conducive to life. These findings have sparked renewed interest in Mars as a potential site for human colonization and a prime candidate in the search for extraterrestrial organisms. But Mars is not the only planet shedding light on the past. Missions exploring the outer reaches of the solar system, such as Juno's study of Jupiter and Cassini's exploration of Saturn, have provided invaluable insights into the formation and evolution of our planetary system. These missions have revealed complex atmospheric dynamics, magnetic fields, and even the geological wonders of icy moons like Europa and Enceladus, moons that may harbor subsurface oceans, offering tantalizing possibilities for life beyond Earth. The drive to explore space continues to push the boundaries of our knowledge, with each new mission expanding our understanding of the solar system and beyond. As we send probes further into the unknown, each discovery builds on the last, furthering our exploration of the cosmos and stoking our insatiable curiosity about what lies beyond the celestial neighborhood we call home. At the heart of these advancements are international collaborations, which are critical to the success of space exploration. These partnerships represent a unified effort to achieve some of humanity's most ambitious scientific objectives. By pooling resources, expertise, and technology from a variety of countries, space missions become more efficient and effective, and they benefit from a wider range of perspectives and problem-solving approaches. No single nation could accomplish these monumental tasks on its own, but by working together, we can tackle the complexities of space exploration more effectively. One of the most remarkable examples of such collaboration is the International Space Station, ISS. This orbiting research laboratory brings together the space agencies of the United States, Russia, Europe, Japan, and Canada. The ISS is not just a hub for scientific experiments, it is a symbol of what can be achieved when nations set aside differences and work toward a common goal. Research conducted aboard the ISS has expanded our understanding of life in space, human health, and advanced technology, revealing the interconnectedness of various scientific disciplines and their potential for advancing both space exploration and life on Earth. As we continue to push the limits of space exploration, these international collaborations will only grow more vital. They offer a blueprint for how the world can unite in pursuit of knowledge, breaking down barriers and reaching new frontiers in our quest to understand the vast, infinite universe we call home. Moreover, international partnerships have become the driving force behind groundbreaking technological advancements that extend far beyond the confines of space exploration. The collaborative efforts between nations not only push the boundaries of science, but also yield innovations that impact life on Earth. Take, for instance, the technologies developed for space missions. These have revolutionized fields like medical imaging, disaster response, and telecommunications. The sharing of knowledge and resources between countries has enabled each to enhance its technical capabilities, fostering an environment ripe with innovation. This collective drive for progress transcends national borders, creating a powerful ripple effect in many industries here on Earth. Perhaps one of the most compelling aspects of international space collaborations is the sense of global unity they inspire. When countries join forces to explore the cosmos, it serves as a reminder of humanity's shared responsibility to protect and preserve our planet, all while reaching for the stars. Space exploration, in its essence, brings people together, uniting them in the pursuit of a common goal. It is this spirit of cooperation that fuels a lasting belief in the power of collective action, inspiring future generations to think beyond geographic and political boundaries. The exploration of space is not only about scientific discovery, but about forging a more cooperative and interconnected world. As technology continues to evolve, one of the most significant breakthroughs in space research has been the rise of artificial intelligence, AI. This cutting-edge technology has revolutionized the way scientists process vast amounts of data, enabling them to analyze and interpret information at an unprecedented speed. Traditionally, the task of analyzing astronomical data was labor-intensive, requiring hours, if not days, of manual work. However, AI has dramatically shortened this time frame, allowing researchers to sift through millions of images and datasets in mere moments. It has the ability to identify patterns and anomalies that may have otherwise been missed by even the most experienced researchers. One area where AI has proven especially transformative is in the detection of exoplanets. By analyzing the subtle light curves of thousands of stars, AI systems can detect the tiny dimming that occurs when a planet passes in front of its star, an event known as a transit. This method, known as the transit photometry technique, has been instrumental in discovering thousands of potential new worlds. Not only does AI accelerate this discovery process, but it also enhances its accuracy, pinpointing the planets most likely to support life. The precision of these algorithms enables scientists to focus their efforts on the most promising candidates, narrowing the vast expanse of space down to a few select worlds that warrant further investigation. In addition to exoplanet discovery, machine learning algorithms are playing a crucial role in the classification of galaxies. AI systems can accurately categorize galaxies based on their shapes, sizes, and types, offering researchers profound insights into cosmic evolution. By organizing galaxies into meaningful categories, AI enables astronomers to connect the dots and develop theories about how the universe has evolved over billions of years. This knowledge is fundamental to understanding the large-scale structures of the cosmos, shedding light on the forces that have shaped the universe we observe today. Looking to the future, AI is poised to become an even more integral part of space exploration. As space missions become increasingly ambitious, such as those aimed at exploring Mars and beyond, the need for autonomous systems will grow. AI-powered systems will be required to make real-time decisions and navigate uncharted terrains, ensuring that each mission can operate independently in environments where human intervention is limited or impossible. By leveraging AI, we are forging a new path in our quest to understand the cosmos, with each discovery bringing us one step closer to unraveling the mysteries of our place in the universe. At the forefront of these efforts are space agencies like NASA and the European Space Agency, ESA, which have set their sights on ambitious objectives that promise to expand our knowledge of the universe. One of the most significant milestones on the horizon is NASA's Artemis program, which aims to return humans to the moon by the mid-2020s. This historic mission will not only land the next astronauts on the lunar surface, but will also include the first woman and the next man to walk on the moon. NASA views this lunar mission not as an end in itself, but as a crucial stepping stone for future missions to Mars and beyond. In parallel, ESA is making strides in its own lunar ambitions. Through its collaboration with NASA on the Artemis program, ESA is contributing critical technologies such as the European Service Module for NASA's Orion spacecraft. Furthermore, ESA is championing sustainable lunar exploration through its Moonlight initiative, which seeks to create a communication and navigation network on the moon to support both governmental and commercial missions. This effort will ensure that the moon remains accessible for decades to come, paving the way for long-term exploration. Mars, too, remains a focal point of exploration. NASA's Perseverance rover, which is already operating on the Martian surface, is tasked with searching for signs of ancient life and collecting samples for future return missions. ESA, in collaboration with other space agencies, is working on the Mars Sample Return mission, which aims to bring Martian soil and rock samples back to Earth for analysis. This project holds the potential not just to answer questions about the existence of life on Mars, but also to unlock secrets about the history of the solar system and the processes that shaped planetary development. Both NASA and ESA are also focused on expanding their reach further into the cosmos. Through initiatives like NASA's James Webb Space Telescope, which is revolutionizing our understanding of the early universe, and ESA's Jupiter Icy Moons Explorer, which is set to explore the habitability of moons like Europa and Ganymede, these agencies are pushing the boundaries of what we know about distant celestial bodies. These missions represent humanity's insatiable curiosity and our unyielding drive to uncover the mysteries of the universe. Astrobiology, the study of life in the universe, is one of the most fascinating fields at the intersection of astrophysics and biology. It aims to answer profound questions about the origins and evolution of life, not just on Earth, but throughout the cosmos. By examining extreme environments on Earth, such as volcanic regions or the deep ocean, scientists are gaining insights into the resilience of life and how organisms might survive in similarly harsh conditions on other planets or moons. Astrobiology also seeks to answer some of the most fundamental questions about life. How does life begin? What makes an environment suitable for life to thrive? It delves into the chemical building blocks of life and how they might form under different cosmic conditions. This multidisciplinary approach enables astrobiologists to predict where life might be found, whether on Mars, the icy moons of Jupiter, or exoplanets in the habitable zones of distant stars. Space missions, telescopes, and laboratory experiments are all vital tools in this search for life. The discovery of water ice on Mars and organic molecules on comets suggests that the building blocks for life might be more common in the universe than we once thought. These findings not only highlight the uniqueness of Earth, but also hint at the possibility that we may not be alone in our ability to support life. As our exploration of the cosmos continues, the quest to answer the age-old question of whether we are alone in the universe remains as urgent and compelling as ever. Astrobiology, a captivating branch of science, delves deeply into the future of life itself. It goes beyond Earth-bound studies to explore the extraordinary ways in which organisms might adapt to diverse and extreme environments on celestial bodies far from our home planet. At the heart of this exploration is a fundamental question: how might life survive and thrive on distant worlds? This inquiry extends to the potential discovery of extraterrestrial life, which could revolutionize our understanding of biology, challenging and expanding what we know about life itself. Through the lens of astrobiology, the mysteries of the cosmos take on a profound significance, reshaping our view of existence both here and across the universe. One of the most awe-inspiring aspects of this field is the way it broadens our understanding of life's possibilities. By examining how organisms might adapt to the harsh conditions of other planets, astrobiology offers a unique window into our own existence, shedding light on how life on Earth might be part of a larger cosmic tapestry. The implications of finding extraterrestrial life, if it exists, are nothing short of revolutionary, opening up entirely new questions about our place in the universe and what it truly means to be alive. To answer these profound questions, scientists in the field of astrobiology employ a variety of cutting-edge tools and techniques to simulate extraterrestrial environments. One of the most common methods is the use of specialized facilities known as planetary simulation chambers. These high-tech chambers can recreate the extreme conditions found on other worlds, whether it's the freezing cold of Mars or the icy moons of Jupiter and Saturn. Within these chambers, researchers can replicate the pressures, temperatures, and atmospheric compositions of distant planets. By adjusting factors such as gravity and radiation levels, scientists can simulate the conditions that extraterrestrial life might face, helping them understand how organisms could potentially survive and evolve in these foreign environments. In addition to these simulation chambers, computer modeling has become an indispensable tool for astrobiologists. Advanced software allows scientists to create highly detailed models of planetary atmospheres and surface interactions. These simulations take into account a wide range of factors, including solar radiation, geological processes, and potential biological activity. By tweaking different variables, researchers can explore an array of scenarios and predict how environments might change over time, helping to shape future missions aimed at uncovering the mysteries of other worlds. Field studies also play an essential role in astrobiological research. Earth-based analog sites, such as the dry valleys of Antarctica or the scorching deserts and volcanic regions, offer invaluable insights into how life might adapt to extreme environments. By studying extremophiles, organisms that thrive in the most hostile conditions on Earth, scientists can gain clues about the potential for life elsewhere in the cosmos. These extremophiles are nothing short of remarkable. They can survive in environments that would be lethal to most other life forms. This resilience not only sparks fascination, but also suggests that life could exist in places previously thought uninhabitable, from the frozen depths of Europa to the boiling surface of Venus. Robotic systems are also becoming increasingly integrated into the study of extraterrestrial environments. These robots, capable of conducting a wide range of experiments, help simulate the conditions of other worlds. From soil analysis to atmospheric sampling, these robotic systems are designed to perform tasks that would be difficult or impossible for humans in such extreme environments. Together with other tools, robots help researchers gather essential data, improving our understanding of potential habitats for life beyond Earth. In the quest to understand extraterrestrial life, astrobiologists focus particularly on life in extreme conditions. On Earth, scientists investigate environments that closely resemble the harsh conditions found on other planets, especially those that orbit far from our sun. These places, like ice-covered lakes, boiling hot springs, deep ocean vents, and high-altitude regions, serve as rich fields for research. By examining the life forms that thrive in these extreme settings, researchers develop models that help them speculate about how life could exist elsewhere in the universe, even under seemingly impossible conditions. One of the most remarkable findings in this field has been the discovery of extremophiles. These extraordinary organisms can survive in environments previously thought to be uninhabitable. For instance, some microbes can endure the crushing pressures and freezing temperatures found in the deep ocean or on the icy surfaces of planets like Mars. Others are able to withstand intense radiation or survive in superheated environments. Such discoveries are groundbreaking because they challenge our very understanding of life's limits. If life can persist under such extreme conditions on Earth, it raises profound questions about its potential existence on other celestial bodies with similar hostile environments. Astrobiologists often take a multidisciplinary approach in their research, drawing on knowledge from microbiology, geology, and environmental science. Field studies in remote and inhospitable locations, such as volcanoes or Arctic tundras, are essential for understanding how life adapts to extreme conditions. By collecting samples from these environments, scientists can analyze how organisms respond to stressors like high radiation or extreme temperature fluctuations. Laboratory experiments, which replicate these extreme conditions, allow researchers to observe how life forms react in real time, offering critical data to evaluate whether similar conditions might support life on other planets. Each new discovery about life's ability to adapt in extreme conditions on Earth not only enhances our understanding of the diversity of life on our own planet, but also directly informs the questions we ask about life in the cosmos. The resilience of life, even in the most hostile environments, provides hope that similar forms of life could exist elsewhere, whether on Mars, Europa, or the many distant exoplanets orbiting stars beyond our solar system. In fact, it is precisely these insights that shape the direction of future astrobiological research as we seek to understand not just how life works, but how it might thrive across the universe. A key discovery that has significantly impacted astrobiology is the identification of water ice on other celestial bodies. Water is a fundamental ingredient for life as we know it, and its presence on worlds like the Moon, Mars, and moons of Jupiter and Saturn offers tantalizing possibilities for the existence of life. The discovery of water ice suggests that these distant locations could harbor environments where life may have existed in the past, or may still exist today. This revelation opens up a wealth of possibilities for further exploration, as it provides scientists with a potential resource for supporting future missions. For instance, if humans establish a long-term presence on Mars, the ability to access local water ice could prove invaluable. Water could be used not just for drinking, but also for producing breathable oxygen and even rocket fuel. In situ resource utilization, ESRU, the process of using local materials rather than bringing everything from Earth, could make long-term missions to Mars and beyond more sustainable. By utilizing the water ice found on these celestial bodies, astronauts could reduce their reliance on Earth-supplied resources, making exploration missions more feasible and allowing humanity to reach further into the cosmos than ever before. Astrobiology, in its quest to explore the potential for life across the universe, touches on some of the most fundamental questions about existence itself. Whether through sophisticated laboratory experiments, field studies in extreme environments, or the search for water ice on distant worlds, scientists are pushing the boundaries of what we know. As these discoveries accumulate, we come ever closer to understanding not only how life could survive on other planets, but also what life truly means in the vast, mysterious expanse of the universe. The presence of ice on celestial bodies across our solar system offers us a crucial glimpse into the ancient history and ongoing evolution of these distant worlds. Water ice, in particular, serves as a time capsule, preserving evidence of past climates, geological processes, and environmental conditions. The distribution and composition of this ice can reveal secrets about the planetary bodies it resides on, shedding light on how these worlds have transformed over eons. By studying these frozen remnants, scientists are gradually piecing together a complex puzzle, uncovering the forces that have shaped planetary development over billions of years. Yet, the significance of ice extends beyond just planetary history. Water is widely considered to be one of the essential ingredients for life, and understanding how it behaves on other worlds brings us one step closer to answering one of humanity's most profound questions. Are we alone in the universe? The search for extraterrestrial water is, in many ways, the search for life itself. When scientists investigate where water ice exists and how it interacts with its surroundings, they are not simply gathering data on temperature and composition. They are formulating hypotheses about how life might or might not thrive in alien environments. These discoveries ignite curiosity, pushing us to look further into the vast cosmos. As we venture deeper into space, the question of life beyond Earth looms ever larger in our exploration efforts, prompting new missions, new technologies, and new hopes for what we might find. But it is not just the search for water that fuels these ambitions. The discovery of complex organic molecules, those fundamental building blocks of life, has profound implications for astrobiology, the scientific field dedicated to understanding the potential for life beyond Earth. Organic molecules like amino acids and hydrocarbons, which are the foundation of biological structures, have been discovered in a variety of places across space. They have been found in interstellar clouds, the icy tails of comets, and even in the atmospheres of distant planets. These findings suggest that the basic ingredients for life are far more abundant than we once thought. Perhaps even more intriguing are the meteorites that have fallen to Earth, containing organic compounds that formed in the vacuum of space long before they collided with our planet. These compounds suggest that the raw materials for life might not be unique to Earth, but widespread throughout the universe. Such discoveries raise compelling questions about the origins of life on our own planet. If the precursors to life were delivered to Earth from space, could this process have occurred elsewhere in the universe as well? Perhaps Earth is not the only place where life could arise. This has only intensified our interest in exploring other celestial bodies that might harbor similar organic molecules. Mars, with its history of liquid water and its surface conditions, is often identified as a prime target for this search. But Mars is far from the only place that holds promise. The moons of Jupiter and Saturn, such as Europa, Ganymede, and Titan, offer tantalizing possibilities, like where organic molecules may exist beneath icy shells or in subsurface oceans. The study of organic molecules in space has also transformed our understanding of the chemical processes that give rise to life. Observations from powerful telescopes have revealed a dynamic and complex pipeline of chemistry unfolding across the cosmos. Simple organic compounds are subject to extreme environments of radiation, heat, and pressure, leading to the formation of more complex molecules. This suggests that the universe acts as a vast laboratory, where the building blocks of life are constantly evolving and interacting. These processes, taking place on a cosmic scale, may be the very foundations upon which life could emerge, wherever the conditions are right. As scientists continue to uncover the secrets of organic chemistry in space, our understanding of the conditions required for life is constantly expanding. Astrobiology now frames life as not just a phenomenon limited to Earth, but a potential reality scattered across the galaxy, waiting to be discovered. The search for extraterrestrial life has shifted from a solitary, Earth-centric pursuit to one that recognizes the widespread availability of the necessary ingredients for life in the cosmos. At the same time, the dream of colonizing other planets has captured humanity's imagination for centuries. Advancements in technology, coupled with an increasing understanding of the challenges posed by space, have made the idea of interplanetary settlements seem less like science fiction and more like a distant but achievable goal. Mars, with its proximity to Earth and certain Earth-like features, such as a day length similar to our own, often stands as the most viable candidate for colonization. However, the reality of establishing a human presence on the red planet is far from simple. Mars presents extreme challenges that would test even the most advanced technologies. The planet's thin atmosphere offers little protection from cosmic radiation, and its surface temperatures fluctuate dramatically, often dropping far below freezing. Colonizing Mars would require innovations that allow us to survive in these harsh conditions. Sustainable habitats capable of shielding humans from radiation would be essential. Growing food in the barren Martian landscape with its lack of liquid water and nutrient-rich soil would require creative solutions. Despite these challenges, the prospect of settling on Mars continues to captivate our collective imagination. Beyond Mars, Moons such as Europa and Titan are also drawing attention for their potential to support life. Europa, with its thick icy shell and the possibility of a liquid ocean beneath, holds particular promise. However, accessing this subsurface ocean and ensuring human survival in such an extreme environment presents hurdles that are currently beyond our technological reach. Similarly, Titan, Saturn's largest moon, has lakes of methane and a thick atmosphere that might offer the conditions necessary for some form of life. Yet, its intense cold and unique chemistry raise difficult questions about the potential for human habitation. While the dream of colonizing other worlds is both exciting and motivating, it remains largely aspirational for the foreseeable future. Space agencies such as NASA, along with private ventures like SpaceX, are pressing forward with their missions, pushing the boundaries of space exploration. However, the path toward making other planets and moons habitable will require not just technological advancements, but also significant international cooperation and, inevitably, ethical considerations. As humanity sets its sights on the stars, a multitude of ethical questions arise. Chief among them is planetary protection, the need to preserve the integrity of other worlds and prevent the contamination of both Earth and extraterrestrial environments. When we send spacecraft to other planets and moons, we risk introducing Earth-based organisms to ecosystems that may be entirely pristine. Additionally, we must consider the potential loss of extraterrestrial life forms that we have not yet discovered. These ethical concerns create a moral imperative to approach space exploration with care, ensuring that our pursuit of knowledge does not inadvertently cause harm to the very places we seek to understand. Another pressing ethical issue is the potential exploitation of space resources. The idea of mining asteroids or extracting materials from other planets raises questions about who has the right to claim these resources. Is space a free-for-all, or should there be regulations in place to ensure that extraction is done in a sustainable and equitable manner? These questions mirror many of the resource conflicts that we face on Earth, urging us to think about how to avoid repeating the same mistakes on a galactic scale. Finally, as we contemplate the prospect of establishing human settlements on other celestial bodies, we must address issues of colonialism. Even if we find no life on a particular planet or moon, the ethical implications of altering landscapes, ecosystems, and environments cannot be ignored. Do we have the right to modify these pristine worlds for our own purposes? This question forces us to define what it means to be responsible, ethical explorers of the universe, especially when we consider our history of exploitation and colonization on Earth. As we extend our reach into the cosmos, we are forced to confront these moral dilemmas and decide what kind of legacy we want to leave, not just for humanity, but for the universe itself. The journey of humanity into space presents profound and multifaceted questions that extend far beyond the boundaries of scientific discovery. As we embark on the grand adventure of exploring the cosmos, we face fundamental choices that will shape not only our exploratory missions, but also the very foundation of a future spacefaring civilization. The governance of our activities beyond Earth will need to reflect a delicate balance between ambition and responsibility, for the decisions made today will echo through the future, potentially influencing everything from the survival of the human race to the ethical implications of extraterrestrial life. Space exploration challenges us not only in terms of technology and resources, but also in the realms of societal values and human resilience. As we venture into the unknown, we must question how to structure the societies that will eventually inhabit new worlds and how to balance the pursuit of knowledge with the preservation of fundamental principles of justice, equality, and sustainability. The choices we make will reverberate for generations, affecting not just the astronauts on the front lines of these missions, but the very character of humanity itself. One of the most fascinating aspects of long-duration space travel is the physical and psychological impact it has on the human body and mind. The microgravity environment of space, so far removed from the familiar pull of Earth's gravity, radically alters the way our bodies function. One of the most noticeable changes is muscle atrophy, Without the constant pull of gravity, muscles weaken, and over time their size diminishes due to disuse. This phenomenon forces astronauts to engage in rigorous exercise regimens while on board, using specialized equipment to maintain their strength and endurance, which is critical not just for mission success, but for their long-term health. In addition to muscle loss, bone density is significantly affected by prolonged time in space. Research has shown that astronauts can lose between 1 to 2% of their bone mass per month while living in microgravity. This bone loss leads to a condition where bones become porous and more prone to fractures, posing a major risk for future missions and the long-term viability of space travel. To combat this, astronauts must adhere to carefully monitored dietary regimens, including an increased intake of calcium and vitamin D, as well as targeted exercise routines designed to minimize bone loss. Despite these precautions, the problem persists and requires ongoing research to develop more effective countermeasures. The mental toll of space travel is equally daunting. Prolonged isolation in confined spaces, separated from family and friends, can lead to a host of psychological challenges. The stresses of living in such a limited environment, coupled with the immense pressure of carrying out high-stakes missions, can lead to feelings of loneliness, anxiety, and depression. Mental health in space is not just a personal concern for astronauts, but a critical issue for mission success. To mitigate these effects, crews are encouraged to maintain regular communication with loved ones back home, engage in recreational activities to relax, and cultivate strong bonds with their fellow crew members to foster a sense of camaraderie and mutual support. Interestingly, space travel also induces a psychological phenomenon known as the overview effect, where astronauts experience a profound shift in their perception of life and the world. From the vantage point of space, the Earth appears as a fragile, beautiful, and interconnected planet, prompting astronauts to rethink their place in the universe. This shift in awareness often leads to a deepened sense of responsibility for the stewardship of Earth, as astronauts gain a new appreciation for the need to protect and preserve our planet for future generations. As science continues to probe the complexities of how space travel affects both the human body and mind, the insights we gain could have far-reaching implications, not just for astronauts, but for our broader understanding of human resilience under extreme conditions. These findings are crucial, not only for the practicalities of space exploration, but also for future missions to more distant worlds, such as Mars, or even further beyond. The prospect of sustaining human life on Mars or other planets demands a suite of groundbreaking technologies. Life support systems will be at the heart of any successful colonization efforts. These systems must be able to provide breathable air, drinking water, and food in a harsh, inhospitable environment. Technologies that can extract water from the Martian soil and atmosphere hold great promise, offering a potential solution for maintaining hydration without relying on Earth-based resupplies. Similarly, advanced recycling systems will need to be developed to purify waste and generate clean air, minimizing the need for resources sent from Earth. Energy production will also be a critical consideration. While solar power seems the most viable option due to the abundance of sunlight on Mars, its effectiveness can be diminished during dust storms, which are frequent on the red planet. As a result, scientists are exploring other alternatives, including more efficient solar panels or even nuclear power systems, which could provide a steady, reliable energy supply in the face of Mars' unpredictable weather. Energy will not only be needed to power machinery and habitats, but also for hydroponic or aeroponic farming, enabling astronauts to grow fresh food on site, thus reducing their dependence on prepackaged food supplies. Radiation protection is another crucial technology that must be addressed. Unlike Earth, which is shielded by a thick atmosphere and a powerful magnetic field, Mars lacks these protective barriers, leaving its surface vulnerable to harmful cosmic radiation. Engineers are working on habitats that incorporate local materials such as Martian regolith, the powdery soil that covers the planet's surface, to provide radiation shielding. These materials offer an innovative and cost-effective means of creating safer living environments for astronauts, while also making use of the resources available on Mars itself. Lastly, The success of future space missions will rely heavily on advancements in communication and transportation technologies. Reliable systems for sending and receiving information between Mars and Earth will be essential for ensuring smooth coordination and decision-making. Additionally, efficient vehicles, such as rovers, drones, and long-range transport systems, will be needed to explore the Martian terrain, gather resources, and lay the groundwork for future settlements. The collective efforts to develop these technologies form an intricate network of systems that, together, will sustain life far beyond the boundaries of Earth. As we continue to push the frontiers of space exploration, the public's interest in these endeavors plays a vital role in shaping the direction of scientific and governmental agendas. When the public shows enthusiasm for space exploration, it often translates into increased funding and support for agencies like NASA and its international counterparts. This widespread interest manifests in popular media, educational programs, and community events, which makes space exploration accessible to people around the world. As more individuals engage with the topics of space travel, they begin to advocate for more ambitious projects, such as manned missions to Mars or the establishment of permanent bases on the Moon. Governments, recognizing the political and economic potential of space exploration, often capitalize on this public fascination. A well-supported space program not only fosters national pride, but also positions a country as a leader in technological innovation. When citizens rally behind space exploration, it can lead to bipartisan support for funding and resources, creating the momentum needed for groundbreaking scientific projects and technological breakthroughs. Thus, the future of space exploration lies not only in the hands of scientists and engineers, but also in the collective will of the global public. As humanity continues its voyage into the stars, the way we govern, support, and understand space exploration will play an increasingly crucial role in shaping not just our destiny in the cosmos, but also the legacy we leave behind on Earth. Public engagement in space exploration has proven to be an invaluable catalyst for inspiring educational initiatives that cultivate the next generation of scientists and engineers. Across the globe, schools are incorporating space-themed curriculums that stimulate students' curiosity about the universe. This educational shift not only fosters a passion for discovery, but also serves as a foundational tool for preparing a highly skilled workforce capable of tackling the complexities and challenges that come with the future of space exploration and technology. As students engage with space-related topics, they develop a sense of wonder about the cosmos. This newfound interest often sparks an ongoing drive for learning, encouraging students to pursue careers in science, technology, engineering, and mathematics STEM. The more these young minds are exposed to space exploration, the more likely they are to develop the skills and mindset needed to innovate and solve the multifaceted problems faced by space agencies and private space companies alike. As a result, the workforce that emerges from these educational programs is not only equipped with technical expertise, but is also driven by the curiosity and enthusiasm necessary to propel the next phase of human space exploration. This wave of public interest in space exploration also has a profound cultural significance. The excitement surrounding space missions permeates various sectors of society, from entertainment to industry, and often inspires cross-disciplinary collaboration. Scientists, engineers, and artists are finding common ground in the pursuit of understanding the universe, leveraging expertise from multiple fields to push the boundaries of space exploration. This collaboration has far-reaching implications, benefiting not just the scientific community, but also inspiring advancements in fields such as robotics, artificial intelligence, and materials science, all of which have practical applications on Earth. Ultimately, this symbiotic relationship between public enthusiasm and government objectives creates a dynamic feedback loop. As public interest fuels scientific inquiry, it generates funding for missions that aim to explore distant planets, moons, and beyond. Successful missions, in turn, spark further fascination, and this cyclical process encourages a continued quest for knowledge. The public's involvement in space exploration thus serves not only to secure funding and political support, but also to generate sustained interest in the mysteries of the cosmos. This ongoing cycle of exploration and discovery highlights the importance of keeping the public engaged, informed, and excited about the wonders of the universe. It ensures that the quest to understand our place in the cosmos remains a shared endeavor, where the triumphs and challenges of space exploration become a part of the collective human experience. At the heart of modern physics, quantum mechanics stands as a towering pillar, yet it is also one of the most enigmatic areas of scientific inquiry. Despite its foundational importance, quantum mechanics remains fraught with perplexities that continue to intrigue scientists around the world. One of the most striking and fundamental principles of quantum mechanics is superposition. In its simplest form, this concept suggests that particles, such as electrons or photons, can exist in multiple states or locations simultaneously until they are observed or measured. This idea challenges our conventional understanding of reality, where we typically expect objects to occupy one distinct state at any given time. To our everyday experience, objects cannot be in two places at once. They are either in one place or another. The famous thought experiment known as Schrödinger's cat vividly illustrates this peculiar phenomenon. In this paradox, a cat inside a sealed box is considered to be both alive and dead at the same time, a state known as a superposition, until someone opens the box and observes the cat. This seemingly impossible scenario serves to highlight just how bizarre and counterintuitive the behavior of particles at the quantum level can be. It also raises questions about the nature of observation and measurement itself. What does it mean for something to exist if we cannot directly observe it? Superposition is just one of the fascinating principles of quantum mechanics. Another equally baffling phenomenon is quantum entanglement. When two particles become entangled, they form a pair in which the state of one particle is instantaneously connected to the state of the other, regardless of the distance that separates them. This is a deeply puzzling concept because it defies the classical understanding of locality, which dictates that information and influence cannot travel faster than the speed of light. Albert Einstein famously described this phenomenon as spooky action at a distance, reflecting his skepticism and confusion about how particles could maintain such a connection over vast separations. The implications of entanglement challenge our classical notions of space and time, suggesting that the universe might be interconnected in ways we are only beginning to understand. How can information travel instantaneously between particles that are light years apart? The fact that entangled particles remain linked in such a way that altering one will affect the other instantaneously calls into question the very fabric of reality as we know it. Adding yet another layer of complexity to quantum mechanics is Heisenberg's uncertainty principle, which states that there are certain pairs of physical properties such as position and momentum that cannot both be measured with absolute precision at the same time. The more accurately one property is determined, the less precisely the other can be known. This is not due to limitations in measurement technology, but is an inherent characteristic of quantum systems themselves. For many, this principle represents a profound shift away from the determinism that once ruled classical physics, as it suggests that the universe at the quantum level is fundamentally probabilistic. Perhaps one of the most mind-bending aspects of quantum mechanics is wave-particle duality. In this phenomenon, particles like electrons and photons can exhibit both wave-like and particle-like behavior, depending on how they are observed. When they are not being observed, they act as waves, existing as probabilities spread out in space. However, when they are measured, they behave as particles occupying specific points in space. This duality, where something can be both a wave and a particle at the same time, confounds our classical understanding of what matter and energy actually are. It suggests that the nature of reality is far more complex than we could have ever imagined, where particles blur the lines between wave-like and particle-like properties, creating a richer and more nuanced understanding of the universe. These quantum principles not only mystify scientists, but also spark ongoing research and philosophical debates about the nature of reality itself. They challenge our deepest intuitions about the world around us and invite us to reconsider the very essence of space, time, and matter. Quantum entanglement, in particular, continues to be one of the most fascinating and perplexing aspects of this field. It highlights an extraordinary connection between two particles that transcends the conventional understanding of space and time. As scientists probe deeper into the nature of quantum mechanics, they are forced to confront the limits of human comprehension and expand their thinking to embrace the truly extraordinary. This ongoing exploration promises to unlock new dimensions of our understanding as it pushes the boundaries of what we know and opens up possibilities that were once thought to be impossible. Quantum entanglement, a cornerstone of quantum mechanics, unveils a profound level of interconnectedness that stretches the limits of human imagination. This intricate phenomenon suggests that at a fundamental level, the universe operates in a manner that defies the separateness we typically observe in our day-to-day experiences. The idea that particles can instantaneously influence one another, regardless of the vast distances between them, challenges our deepest assumptions about space, time, and causality. Such entanglement stirs a sense of awe as it invites us to reconsider the nature of reality itself. Are we living in a universe made up of isolated, independent objects, or is the cosmos in its essence a seamless and interconnected web that eludes our intuitive understanding? The implications of quantum entanglement stretch far beyond the confines of theoretical physics, offering the foundation for some of the most groundbreaking technologies of our time. Emerging fields such as quantum computing and quantum cryptography are built upon the very principles that quantum entanglement highlights. These technologies, still in their infancy, promise to revolutionize how we process information and secure communications, potentially transforming industries from banking to healthcare. But with every new discovery, we are forced to grapple with paradoxes that challenge our most basic beliefs about reality. As our understanding of the quantum world expands, we find ourselves rethinking not only how we comprehend the universe, but also our place within it. One of the most striking and mysterious aspects of quantum physics is the observer effect, which reveals that the very act of observation can shape the reality we perceive. At the microscopic scale, this phenomenon becomes even more profound. In simple terms, the observer effect suggests that when we attempt to measure or observe certain quantum systems, such as particles, our observation alters their behavior. The presence of the observer is not a passive act. Rather, it actively interacts with the system, influencing its state. For example, when scientists measure the position of an electron, the act of observation itself can cause the electron to shift from its original location. This interaction doesn't just complicate our understanding of quantum mechanics, it shatters the notion that the universe behaves predictably or deterministically. Such revelations invite us to ask deeper questions. Are we, as conscious beings, playing a role in shaping the outcomes of quantum events? Or is there an underlying objective reality that exists independent of our measurements and perceptions? These questions are not merely theoretical. They have practical implications for emerging technologies like quantum computing and cryptography, which seek to harness the very phenomena that quantum mechanics has uncovered. The observer effect underscores the idea that, at its most fundamental level, the universe does not behave in ways we can easily understand. It challenges us to reconsider the nature of reality, pushing the boundaries of science and philosophy. Moreover, the intertwining of quantum mechanics with cosmology, the study of the universe's largest structures, provides an even richer narrative. These two fields at first glance seem worlds apart. Quantum mechanics delves into the behavior of particles on infinitesimally small scales, while cosmology explores the vastness of space and time. However, the convergence of these disciplines brings to light some of the most perplexing and significant questions about the nature of existence. One particularly intriguing intersection lies in the study of the early universe, immediately following the Big Bang. It is believed that quantum fluctuations arising from the uncertainty principle played a crucial role in shaping the distribution of matter and energy that would eventually give rise to galaxies, stars, and planets. These fluctuations reflect the inherent unpredictability of the quantum world, with particles seemingly emerging out of the vacuum of space before vanishing again, an idea that upends classical notions of the void. Cosmic inflation, the rapid expansion of the universe just after the Big Bang, further intertwines quantum theory with the fabric of the cosmos. According to inflationary theory, minuscule quantum fluctuations were stretched across the vast expanse of space during this period of hyperexpansion, ultimately giving rise to the large-scale structures we observe today. This theory suggests that the very genesis of the universe itself was deeply influenced by quantum processes, a perspective that demands we reconsider the role of quantum mechanics in our models of cosmological evolution. Without incorporating quantum principles, our understanding of the universe's origins remains incomplete. Yet the quest to unify the realms of quantum mechanics with that of general relativity, the theory that governs the behavior of large-scale cosmic phenomena like gravity, remains one of the most daunting challenges in modern physics. Theoretical frameworks such as string theory and loop quantum gravity attempt to bridge these two domains, but as of now, no definitive theory has emerged. A successful unification could not only provide deeper insights into the nature of black holes, but also shed light on some of the most profound mysteries in cosmology: dark matter and dark energy, the unseen forces that dominate the universe's structure and expansion. The pursuit of this theory of everything could forever alter our understanding of space, time, and the fundamental laws that govern the universe. At the cutting edge of technology, quantum computing promises to redefine what is possible in terms of data processing and computation. Unlike classical computers, which store and process information in binary form as either a 0 or a 1, quantum computers leverage the unique properties of quantum bits, or qubits. These qubits are not confined to a single state. They can exist in multiple states simultaneously, thanks to the principle of superposition. This allows quantum computers to perform calculations at speeds unimaginable with current technologies, tackling problems that would be impossible for even the most powerful classical computers to handle. One of the most promising applications of quantum computing lies in its potential to simulate quantum systems themselves. Since the universe operates according to the principles of quantum mechanics, many natural phenomena, from the behavior of elementary particles to the interactions within complex materials, cannot be adequately modeled using traditional computational methods. Quantum computers, however, could simulate these quantum interactions with unprecedented accuracy, offering insights into everything from the properties of matter and the nature of chemical reactions to the formation of galaxies. As we unlock the mysteries of the quantum world, we move closer to a future where we can truly understand and perhaps even control the very fabric of reality. Quantum computing represents an exciting frontier, one with the potential to revolutionize how we approach some of the most profound questions about our universe. As this technology matures, it could become a cornerstone in solving complex problems that currently stretch the limits of human comprehension. Fields like cosmology and particle physics, where vast amounts of data are routinely generated, stand to benefit enormously. Quantum computers, with their unmatched processing power, will be able to analyze these datasets at speeds and accuracies far beyond what classical computers can achieve. This will allow scientists to identify subtle patterns and relationships hidden within the data, pushing forward our understanding of fundamental forces. One of the most intriguing prospects is how quantum computing could help unravel the mysteries of dark matter and dark energy. These two enigmatic forces account for the vast majority of the universe's mass and energy, yet they remain largely invisible and elusive to traditional methods of observation. Through quantum-enhanced analysis of particle accelerator data, quantum computers could unlock new insights into these cosmic phenomena, potentially transforming our view of the universe. As quantum computing continues to evolve, it holds the promise of enabling breakthroughs that may redefine our understanding of the cosmos itself. By embracing the principles of quantum mechanics, this technology could one day answer questions about the very fabric of reality and the origins of existence. But the potential of quantum computing extends beyond just theoretical exploration. It could also drive real-world innovations that reshape our approach to sustainability here on Earth. The universe operates on a delicate balance, where forces and matter interact in harmony. This balance is evident in the movements of celestial bodies, the fusion processes powering stars, and the gravitational forces that govern planetary systems. Understanding these cosmic interactions offers profound lessons on the importance of balance in our own world, particularly when it comes to environmental stewardship. Much like the stars that maintain their delicate equilibrium through fusion and gravitational pull, Earth's ecosystems rely on interconnected cycles to function properly. The carbon cycle is a prime example, where carbon moves between the atmosphere, oceans, and living organisms, ensuring that our planet's systems remain stable. In this way, the health of our ecosystems mirrors the cosmic balances we observe in space. If we over-extract natural resources or disrupt vital habitats, we risk tipping the scales, much like the catastrophic effects of a celestial body disrupted by gravitational forces. Furthermore, the concept of resilience, which is seen in the universe's ability to evolve and adapt, can serve as a model for how we address challenges on Earth. Stars undergo dramatic transformations, often exploding in supernovae, enriching the universe with essential elements for life. Planets, too, develop unique systems that support a diverse array of life forms. These processes offer us valuable lessons on how to cultivate resilience within our urban and agricultural environments. By fostering biodiversity, adopting regenerative farming techniques, and investing in renewable energy, we can create systems that thrive despite changing conditions, much like the dynamic systems observed in space. Incorporating the lessons of cosmic balance into our understanding of sustainability requires us to embrace a holistic view. It's not enough to focus on individual components of the environment. We must recognize the complex, interwoven relationships that bind everything together. This perspective encourages a more integrated approach to conservation, technological innovation, and sustainable practices. By learning from the universe's balanced systems, we can work toward a future that harmonizes with the natural world, ensuring that our planet remains healthy and vibrant for generations to come. The drive towards sustainable living has gained significant momentum in recent years, spurred by the urgent need to address climate change and the depletion of natural resources. Among the most promising developments in this area are advancements in renewable energy technologies. Solar panels, once limited by efficiency issues, have seen dramatic improvements in design, allowing them to capture sunlight even under less than ideal conditions. Similarly, wind turbines have grown in size and efficiency with larger blades and more aerodynamic designs, enabling them to generate energy even at lower wind speeds. These innovations are essential in reducing our dependence on fossil fuels and accelerating the shift toward cleaner, more sustainable energy sources. In the realm of agriculture, the rise of vertical farming has emerged as a groundbreaking solution to the challenges posed by traditional farming methods. By utilizing multi-story buildings, vertical farms can grow crops in a controlled environment, minimizing the need for vast expanses of land and drastically reducing water consumption. With the use of hydroponics and aeroponics, farmers can cultivate fresh produce year-round while significantly lowering their carbon footprint. In fact, vertical farming systems use up to 90% less water than conventional farming, showcasing their potential to foster both sustainability and food security. Urban areas are also beginning to embrace innovative approaches to sustainability, particularly through the integration of smart city technologies. These systems use data and sensors to optimize energy use, streamline waste management, and improve public transportation. Smart grids, for example, can dynamically adjust energy distribution based on demand, reducing reliance on fossil fuels while increasing efficiency. In addition, some cities are installing green roofs and walls, which not only improve insulation and reduce energy consumption, but also promote biodiversity and help mitigate the urban heat island effect. In the field of material science, new breakthroughs are making it possible to reduce waste and promote sustainability through the development of biodegradable plastics and advanced recycling technologies. These materials, made from natural sources, break down more easily in the environment, helping to curb plastic pollution and its harmful effects on ecosystems. As these technologies continue to evolve and gain traction, they offer a promising solution to one of the most pressing environmental challenges of our time. However, the most significant advancements in sustainability will come from a deeper understanding of Earth's ecosystems, which are integral to regulating the planet's climate. Ecosystems, which consist of complex networks of living organisms interacting with their physical environment, play a crucial role in maintaining the planet's climate stability. By studying these ecosystems, scientists can better understand how changes in climate affect biodiversity and, conversely, how healthy ecosystems can mitigate the impacts of climate change. Forests, for instance, serve as significant carbon sinks, absorbing carbon dioxide from the atmosphere and storing it in trees, plants, and soil. By understanding the dynamics of forest ecosystems, we can take more informed actions, such as reforestation and sustainable forest management, to enhance their carbon storage capacity. This will help ensure that these ecosystems continue to absorb greenhouse gases rather than releasing them, a critical step in the fight against rising global temperatures. Wetlands, too, play an essential role in carbon sequestration, flood protection, and water filtration. Protecting and restoring these vital ecosystems will not only help mitigate climate change, but also ensure the continued availability of clean water and the preservation of biodiversity. Every ecosystem, from oceans to grasslands, contributes uniquely to this global climate puzzle, and understanding their roles will enable us to implement more effective conservation and restoration strategies. As we continue to develop new technologies and deepen our understanding of the planet's ecosystems, the journey toward a sustainable future becomes not just a possibility, but a tangible reality. The interplay of science, technology, and ecological knowledge provides the tools we need to combat climate change and ensure the longevity of life on Earth. Ultimately, the lessons of balance, resilience, and interconnectedness, drawn from both the universe and our own planet, will guide us toward a future where sustainability and harmony are not just goals, but realities we can achieve. Ecosystems, often unseen in their daily workings, provide invaluable services that support the foundation of life on Earth. These natural systems offer us the essentials: food security, clean water, and numerous health benefits. A well-functioning ecosystem does much more than sustain life. It enhances our resilience to climate change, offering a stable platform from which we can adapt to the challenges ahead. As we face an increasingly uncertain environmental future, the need to harmonize our interactions with the natural world has shifted from a choice to a critical necessity for our very survival. At the heart of this transition is the rise of renewable energy technologies, poised to become cornerstones in shaping a sustainable future for humanity. As the world grapples with the dual challenges of climate change and the dwindling reserves of fossil fuels, these technologies provide a much-needed lifeline. They not only offer a sustainable alternative to traditional energy sources, but also promise to reduce harmful greenhouse gas emissions, foster energy independence, and stimulate economic growth. Wind, solar, hydroelectric, and geothermal power are leading the way, each harnessing the Earth's abundant natural resources in ways that minimize their environmental footprint. Among these, solar energy stands out as a remarkable example of progress. Over the past few decades, it has experienced a dramatic expansion. With advancements in photovoltaic cell technology and improved battery storage systems, solar energy can now be generated even in less than ideal conditions. This means that clean electricity can reach homes and businesses in remote or cloudy regions where solar power was once considered unfeasible. Meanwhile, wind energy has similarly transformed landscapes, with vast wind farms dotting the horizon, each turbine quietly generating clean energy. Not only do these farms produce power, but they also bring jobs and economic stimulation to local communities, fostering a deeper sense of connection to the energy they consume. These renewable technologies do more than just generate electricity. They are sparking a revolution in energy storage, grid management, and innovation. As solar and wind power become more integrated into the global energy mix, they are paving the way for a more resilient and decentralized energy infrastructure. This shift away from centralized, polluting power plants is vital in reducing air pollution and improving the health of populations, particularly in urban centers, where the impact of fossil fuel emissions is felt most acutely. Moreover, the rise of renewables is prompting a broader shift in how we approach energy consumption. With renewable energy becoming more accessible, there's a growing trend toward efficiency and sustainable practices. Communities are taking a more active role in their energy needs, with residential, solar installations, and community-based wind projects becoming increasingly common. This decentralized approach to energy production not only reduces reliance on large-scale polluting power plants, but also empowers local communities to take charge of their energy future, leading to a cleaner, healthier planet. As we look to the future, continued investment in renewable energy research and development will be essential. Governments and businesses around the world are recognizing that innovation in this sector is not just a moral imperative, but also an economic one. The transition to a green economy offers opportunities for new industries, jobs, and technologies that can drive global economic stability. As technology continues to evolve, we can anticipate a world where renewable energy is no longer viewed as an alternative, but as the primary source of power that propels us toward a sustainable, prosperous future on Earth. Yet, alongside this technological revolution, conservation efforts remain equally vital in ensuring that our planet's natural resources are preserved for future generations. At the core of conservation is responsible resource management, a principle that aims to ensure that essential resources such as water, forests, and wildlife are used sustainably. This approach allows us to benefit from these resources today without compromising their availability for the future. Through thoughtful and proactive conservation efforts, we can balance human needs with the preservation of biodiversity, ensuring the resilience of ecosystems that provide vital services to our communities. Conservation initiatives, particularly those aimed at protecting biodiversity, play a crucial role in sustaining the intricate web of life that sustains us. Healthy ecosystems are not only a source of beauty, but also provide essential services like clean air, water filtration, and the pollination of crops. When we protect habitats from destruction and pollution, we safeguard not only wildlife, but also the complex interdependencies that support human life. The decline of any species can trigger a cascade of effects throughout the ecosystem, emphasizing the need for vigilance in conservation efforts. In the end, the future of life on Earth hinges on the delicate balance between technological innovation and environmental stewardship. By embracing renewable energy, reducing our ecological footprint, and committing to the protection of our planet's natural systems, we can ensure a future that is both sustainable and prosperous for generations to come. Furthermore, conservation strategies often place a significant emphasis on the restoration of areas that have been severely degraded. A prime example of such an effort is reforestation, which focuses on planting new trees in places where forests have been depleted or destroyed. This initiative does more than just restore habitats. It actively contributes to carbon capture, a vital process in combating climate change. The trees absorb carbon dioxide from the atmosphere, playing a key role in mitigating the warming of our planet. By investing in these rehabilitative efforts, we are not only replenishing the Earth's natural resources, but also promoting a continuous cycle of renewal that benefits all living organisms. This dynamic process fosters a more balanced ecosystem where biodiversity can thrive once again. Moreover, conservation efforts often engage and empower local communities. Involving these populations in the management of natural resources strengthens the bond between people and the land. Communities who directly rely on these resources are more likely to adopt sustainable practices as they become stewards of their environment. Such grassroots initiatives have proven to be effective in fostering a deeper sense of responsibility and ownership over local ecosystems. As we look to the future, aligning conservation efforts with resource management will be crucial for ensuring not only the survival of the planet's ecosystems, but also the well-being of human populations. The interdependence between nature and humanity will define the trajectory of a thriving, sustainable world. Throughout history, cultures across the globe have turned their gaze upward, looking to the stars and celestial bodies with a sense of awe and wonder. The night sky has long been a source of inspiration, with societies using the movement of stars, planets, and natural phenomena to shape their worldview. These cosmic forces were often personified or viewed as divine entities, believed to hold great power over human lives and earthly events. For example, ancient Egyptians revered the sun god Ra, who was seen as the embodiment of life and light. Meanwhile, the Greeks crafted elaborate myths around the planets, personifying them as gods and goddesses whose actions directly influence the fate of humans. These interpretations provided a divine framework that helped to explain not only the mysteries of the universe, but also the complexities of the human experience. As societies progressed, so too did our understanding of the cosmos. The Renaissance ushered in an era of scientific inquiry, fundamentally altering how humans viewed the heavens. Figures such as Nicolaus Copernicus proposed the revolutionary idea that the Earth revolves around the Sun, challenging the long-held belief that the Earth was the center of the universe. This heliocentric theory sparked a wave of debates and discoveries that led to the scientific revolution, a transformative period that redefined humanity's place in the cosmos. The cosmos, once considered a realm of myth and mystery, gradually transformed into a subject of rigorous study. This shift marked the beginning of a new era where celestial bodies were understood not as divine entities, but as physical objects governed by natural laws. The human understanding of the universe had moved from the realm of the spiritual to the empirical, paving the way for modern science. In recent centuries, technological advancements have further deepened our connection to the cosmos. The development of telescopes has expanded our view of the universe, allowing us to observe distant galaxies and the faint whispers of cosmic radiation that tell the story of the universe's origins. Scientific theories, such as the Big Bang, have provided a narrative that explains the birth of the universe, blending cultural interpretations with observable evidence. This merging of scientific discovery with cultural narratives has allowed us to appreciate the universe not just as a vast, impersonal expanse, but as a backdrop to human existence. The cosmos has evolved into something far more than just a distant sky. It now serves as a canvas on which humanity projects its hopes, fears, and aspirations. Today, cultural interpretations of the cosmos continue to evolve alongside scientific understanding. The exploration of life beyond Earth, astrobiology, the search for extraterrestrial intelligence, and the ongoing fascination with planets and moons has entered the mainstream. This curiosity about what lies beyond our planet has taken root in popular discourse, with scientific and speculative ideas often blending together. Modern storytelling in film, literature, and art reflects these themes, fueling our imaginations and sparking discussions about humanity's place within this vast universe. What was once the domain of myth and mysticism is now a cultural touchstone, shaping how we think about life, the universe, and everything in between. The cosmos has become a reflection of ourselves, a place where we confront our collective dreams and existential questions. We no longer just observe the stars, we actively engage with them, seeking answers to some of humanity's most profound mysteries. Throughout history, astronomical discoveries have had a profound impact on human culture. When ancient civilizations first began turning their eyes to the heavens, they saw the movements of celestial bodies as direct influences on their lives. The rise of agriculture, for example, was tightly intertwined with the movements of the sun and moon, as early farmers used these celestial markers to predict seasonal changes and guide planting and harvesting cycles. As human societies evolved, the stars became more than just navigational tools. They became the foundation for rich mythologies. Constellations were not merely patterns in the sky, but symbolic stories that explained the mysteries of life and our place in the world. The celestial realm was as much a part of cultural identity as it was a tool for survival. The early 17th century marked a pivotal moment in the history of astronomy, as the invention of powerful telescopes allowed for the first time a deeper look into the cosmos. Galileo Galilei, in particular, made groundbreaking discoveries that radically transformed our understanding of the universe. His observations of the moons of Jupiter and the phases of Venus directly challenged the long-held geocentric view of the cosmos, which placed Earth at the center of the universe. This realization that the Earth was not the center of everything shattered long-standing beliefs and set in motion a broader intellectual revolution. The implications of this discovery went far beyond astronomy. They sparked a wave of curiosity and inquiry that contributed to the Enlightenment, influencing philosophy, art, and religion. Humanity's conception of its place in the universe was forever altered. In the contemporary era, the ongoing exploration of our solar system and the discovery of exoplanets continue to shape the cultural landscape. The idea that life may exist beyond Earth has captivated human imagination and inspired entire genres of literature, film, and art. From science fiction movies to television shows, the possibility of life beyond our planet is a central theme, weaving astronomical concepts into popular culture and encouraging an ongoing fascination with the cosmos. The search for extraterrestrial intelligence has sparked a renewed sense of wonder, with humanity now asking fundamental questions about what it means to be human and what our role in the universe might be. In this age of exploration, the cosmos has become a mirror, reflecting not just the unknown, but the deepest aspirations of human curiosity and creativity. It is both a mystery and a mirror, forever inviting us to explore, discover, and dream. As humanity ventures deeper into the cosmos, the discoveries we make not only expand our understanding of the universe, but also ignite profound philosophical reflections on our existence and our place within the vast expanse of space. The Hubble Space Telescope, a beacon of modern astronomical exploration, has provided breathtaking images that do more than just reveal the mesmerizing beauty of the cosmos. They serve as a humbling reminder of our own insignificance in the grand scale of the universe. These revelations have fostered a renewed sense of wonder and a profound responsibility towards our planet and beyond. As we reach for the stars, we are reminded that in our pursuit of cosmic understanding, we must also nurture and protect the fragile world we call home. Science does not exist in a vacuum. It is deeply intertwined with culture, shaping and being shaped by the values, beliefs, and priorities of the societies in which it is practiced. Every scientist is influenced by the specific cultural and social context in which they live, and this context often dictates the questions they ask, the methods they employ, and the interpretations they make from their findings. Cultural influences can determine the scientific issues that are deemed most relevant, with different societies focusing on problems that resonate most with their unique circumstances. For example, environmental concerns may take center stage in societies grappling with climate change, while health issues might dominate in regions struggling with disease outbreaks. This dynamic interaction between science and culture highlights the importance of understanding how cultural perspectives shape scientific inquiry. In many cases, cultural beliefs can also influence how scientific findings are received. Discoveries that challenge widely held views may face skepticism or outright rejection. This is particularly evident in debates around climate change, where cultural attitudes and political ideologies have a profound effect on public acceptance and policymaking. The resistance to accepting scientific consensus can hinder progress and delay critical actions needed to address global challenges. Yet, despite these challenges, the ongoing dialogue between science and culture remains vital for advancing knowledge and fostering mutual understanding. Embracing diverse cultural perspectives not only enriches the scientific process, but also fosters innovation by challenging prevailing assumptions and encouraging new ways of thinking. One powerful example of this is the field of ethnobiology, where the traditional knowledge of indigenous cultures has contributed invaluable insights into biodiversity and ecosystem management. These communities have long recognized patterns and relationships within nature that modern science is only beginning to fully appreciate. When scientists collaborate with indigenous peoples, they often uncover knowledge that would have been overlooked by conventional scientific methods, expanding our understanding of the natural world. In this way, cultural diversity becomes a critical resource for enriching scientific inquiry and expanding the horizons of what is possible. As we look to the future, it is increasingly clear that science today is a global endeavor. Collaborative projects that span multiple cultures and regions have become the driving force behind many of the most innovative solutions to the complex problems we face. These international partnerships facilitate the exchange of ideas, perspectives, and methodologies, resulting in more comprehensive and effective approaches to challenges such as climate change, public health, and space exploration. By embracing this cultural diversity, we not only enhance the scientific process, but also ensure that the knowledge we create is more inclusive and reflective of our shared humanity. Space exploration, in particular, has had a profound impact on art and literature, blending the realms of science and creativity in ways that captivate the imagination. As humanity has reached for the stars, artists and writers have sought to capture the awe, wonder, and existential questions that accompany our quest to understand the universe. The imagery of space, vast galaxies, distant planets, and strange landscapes has become a canvas for exploring deeper themes of existence, identity, and the future of humanity. From the earliest days of rocketry, authors like H.G. Wells and Jules Verne envisioned journeys to the moon and beyond, pushing the boundaries of imagination at a time when such expeditions seemed purely fantastical. Their works laid the foundation for a genre that would grow exponentially as real space missions brought the wonders of the universe into sharper focus. In 2001, A Space Odyssey, Arthur C. Clarke not only predicted future technological advances, but also prompted thought-provoking discussions about artificial intelligence and the nature of consciousness, ideas that are becoming ever more relevant as our technological capabilities evolve. Visual artists, too, have been inspired by the exploration of space. Pioneers like Chesley Bonestell, whose illustrations in the 1950s redefined astronomical art, brought to life the ringed beauty of Saturn and the rugged landscapes of Mars. His work inspired generations of scientists and dreamers, shaping public perceptions of space and sparking interest in the scientific questions that lay behind it. Today, contemporary artists use data from space missions to create striking visual representations of scientific discoveries, bridging the gap between the world of science and the realm of artistic expression. These pieces not only resonate with art enthusiasts, but also spark curiosity in those eager to understand the scientific phenomena behind them. As space exploration becomes more accessible, both literature and art have turned their focus to themes of personal exploration and the human connection to the cosmos. Works inspired by the experiences of astronauts or the technological marvels of space shuttles add an emotional and philosophical layer to our ventures beyond Earth. These works ask us to reflect on the human spirit, the sense of wonder that drives us, and the profound questions that arise when we leave the familiar Earth behind. The ongoing dialogue between science and art deepens our appreciation of the universe, reminding us that exploration is not just about reaching new frontiers, but also about grappling with the profound questions of existence that such journeys inspire. As we look to the stars, we are not just charting the unknown, we are exploring the very nature of what it means to be human. The universe, vast and mysterious, is filled with unanswered questions that continue to captivate scientists. One of the most perplexing enigmas is dark matter. Although dark matter makes up about 27% of the universe's mass energy content, it remains invisible to our instruments. Its presence is inferred through the gravitational effects it exerts on visible matter, such as galaxies, yet its true nature is still unknown. Scientists are exploring various theories, including the possibility that dark matter consists of exotic particles that interact only weakly with ordinary matter, making it nearly undetectable. Another profound mystery is dark energy, the force believed to be responsible for the accelerated expansion of the universe. Dark energy makes up approximately 70% of the universe, yet its composition and fundamental properties are still unfathomable. Its existence raises profound questions about the future of the universe. Will it continue to expand indefinitely, or will it one day slow, halt, and reverse? Understanding dark energy is one of the greatest challenges facing modern cosmology. Perhaps most fascinating of all are the black holes, regions in space where gravity is so intense that nothing, not even light, can escape. These cosmic giants warp space and time itself, yet the physics that govern them remain elusive. Recent discoveries, such as the detection of gravitational waves caused by colliding black holes, have opened a new frontier in our understanding of these mysterious entities. As scientists delve deeper into the behavior of black holes, they face questions that push the limits of our knowledge, such as the nature of singularities and the event horizon. Each new discovery brings us closer to unlocking the secrets of these enigmatic objects and expanding the boundaries of our understanding of the universe. The mystery of alien life continues to captivate not only scientists but humanity as a whole. The boundless expanse of the cosmos makes it difficult to believe that we are the only ones here, despite decades of searching and the countless discoveries of exoplanets in recent years. Yet, even with all these advancements, we have yet to find definitive proof of extraterrestrial life. Every new planet discovered in the so-called habitable zone seems to raise more questions than it answers. Are we on the cusp of discovering life beyond Earth, or are we merely passive observers in an empty, cosmic wilderness? The quest for answers to these questions is far from over, driving explorers, scientists, and dreamers to push the boundaries of what we know about the universe. As we cast our gaze deeper into the heavens, countless frontiers in exploration beckon us forward, challenging us to uncover new cosmic phenomena and unravel mysteries that have long remained hidden. Among these frontiers, one stands out as a cornerstone of modern astronomy: the advancement of next-generation telescopes. Instruments like the James Webb Space Telescope, for example, are already transforming our understanding of the cosmos. Unlike its predecessors, Webb is designed to observe infrared light, allowing it to peer deeper into space and further back in time than ever before. This capability opens up new vistas of exploration, revealing distant exoplanets, ancient galaxies, and the building blocks of stars and planets. With these discoveries, Webb holds the promise of revealing phenomena that we have yet to even imagine, including potential insights into the origins of the universe itself. Another frontier of immense excitement lies in the realm of gravitational wave astronomy. The detection of gravitational waves, ripples in the fabric of space-time caused by cataclysmic events like black hole mergers, has ushered in a new era of cosmic observation. Upcoming observatories, such as the European Space Agency's LISA mission, aim to detect low-frequency gravitational waves, offering us a unique window into the most violent and energetic events in the universe. These waves could help unlock mysteries about black holes, neutron stars, and even the very nature of space-time itself. The implications of this research are profound, as it may challenge existing theories in astrophysics, providing fresh perspectives on the fundamental forces that shape our universe. In addition to the exploration of distant cosmic phenomena, our understanding of our own solar system is expanding at a rapid pace. Missions to the outer reaches of the solar system, including the ongoing exploration of Mars and the study of Jupiter and Saturn's moons, are rapidly expanding our knowledge of these celestial bodies. A particularly exciting development is the recent launch of NASA's Europa Clipper mission, designed to investigate the habitability of Jupiter's icy moon Europa. Europa is believed to harbor a subsurface ocean beneath its frozen exterior, and finding signs of life in these alien oceans would represent a monumental leap forward in our understanding of life's potential existence beyond Earth. Equally compelling is the study of dark matter and dark energy, two elusive and largely invisible components of the cosmos. New, powerful surveys and cutting-edge particle physics experiments are underway to detect direct evidence of dark matter particles. The nature of dark matter and dark energy holds the key to understanding the expansion of the universe and could help bridge critical gaps in our current scientific models. The implications of these studies extend far beyond our understanding of the cosmos. They could provide answers to some of the most fundamental questions about the universe's composition and evolution. The frontiers of exploration in the cosmos are vast and beckon us to push further than we have ever gone before. Yet the scope of our potential discoveries is not confined solely to space. As we look ahead, the potential for future scientific breakthroughs to reshape our understanding of life and the universe is immense. Advances in fields like genetics, artificial intelligence, and quantum physics could open entirely new doors to understanding existence itself. In the realm of genetics, the ability to decode the intricacies of life at a molecular level holds enormous promise. These advancements could lead to revolutionary insights into the nature of living organisms, how they emerge, evolve, and interact with the universe. One area showing significant promise is biotechnology. As we enhance our ability to edit genes and manipulate biological systems, we may soon discover entirely new forms of life. In fact, synthetic biology could enable us to create organisms that thrive in extreme environments once thought inhospitable to life. This breakthrough could not only redefine our understanding of life on Earth, but could also inform our search for extraterrestrial life, particularly in environments previously considered uninhabitable. Simultaneously, as we push the boundaries of artificial intelligence, we are on the brink of redefining consciousness and intelligence itself. The development of advanced AI opens up the possibility of interacting with non-biological forms of consciousness. This would challenge our very definitions of sentience, forcing us to ask profound questions about the nature of consciousness. Could a non-biological entity possess self-awareness? Could consciousness exist independently of a biological substrate? These questions will not only shape our understanding of what it means to be alive, but could also revolutionize how we interact with technology, potentially changing our relationship with machines forever. As we continue to explore both the vastness of the universe and the potential within ourselves, one thing is certain: the future of science holds unimaginable possibilities. Whether we are peering into the farthest reaches of space, unlocking the secrets of life's molecular code, or creating intelligent systems that challenge the very fabric of our understanding of consciousness, humanity stands on the threshold of a new era, one filled with mystery, discovery, and the promise of answers to questions that have long eluded us. The pursuit of knowledge, both of the cosmos and of ourselves, will continue to push the limits of what we know and what we can imagine. Advancements in astrophysics, particularly in the study of dark matter and dark energy, are poised to radically alter our understanding of the cosmos. As scientists continue to delve into the fundamental forces that govern the universe, they are uncovering potential links between the microscopic and the vast expanse of space itself. These discoveries promise to illuminate not only the invisible forces that shape the fabric of the universe, but also the very origins of life and our ultimate place within this awe-inspiring and mysterious expanse. The future of scientific exploration holds a treasure trove of tantalizing possibilities, each one pushing the boundaries of what we know and expanding the grand tapestry of knowledge about both life and the universe in ways we can scarcely begin to imagine. Among the most captivating questions that continue to captivate our collective curiosity is the search for life beyond Earth. The idea of life thriving elsewhere in the universe raises profound questions that elicit both wonder and skepticism. One of the most urgent and compelling inquiries is whether life could exist in environments vastly different from those on Earth. Scientists are particularly keen to investigate the potential for life in the thick, toxic clouds of Venus. Here, sulfuric acid and crushing atmospheric pressure create conditions so hostile that they seem utterly inhospitable to life as we know it. And yet some researchers speculate that microbial life could still exist, sheltered in the planet's more temperate upper cloud layers, or perhaps in pockets of atmosphere where conditions might support biological processes. The very notion pushes the boundaries of our understanding of life's adaptability. Meanwhile, moons like Europa and Enceladus, which orbit the gas giants Jupiter and Saturn respectively, present even more intriguing possibilities. These moons, with their hidden subsurface oceans beneath thick layers of ice, could harbor the potential for life. The questions that arise are numerous. What kind of organisms might survive in these alien aquatic environments? Could they be similar to extremophiles, the hardy organisms found in the most inhospitable regions of our own planet? These moons, once thought to be barren wastelands, are now at the center of astrobiological studies with the potential for groundbreaking discoveries just beyond the horizon. Even more fascinating is the search for intelligent life elsewhere in the cosmos. If advanced civilizations do exist, will we ever be able to make contact? This question is at the heart of the Fermi paradox, which underscores the tension between the vast number of stars and potentially habitable planets scattered across the universe and the conspicuous absence of detectable signals from other intelligent beings. Given the enormity of the cosmos, why haven't we encountered any definitive signs of extraterrestrial intelligence? Moreover, understanding the very building blocks of life serves as a cornerstone for these grand inquiries. Scientists are exploring how organic molecules, those essential building blocks for life, form in space. Could these molecules be the seeds that might spark life on other planets under the right conditions? As technology advances and our methods of investigation grow ever more sophisticated, we are also delving into how these building blocks travel across space, potentially carried on comets or through interstellar dust. Astrobiologists are particularly excited about the potential for extremophiles, organisms that thrive in harsh, Earth-like environments. These creatures could offer us vital clues about the kinds of life forms that might persist in extreme conditions on distant worlds. As our technological capabilities continue to evolve, so too does our ability to explore these profound questions. Manned missions to Mars, the exploration of the outer moons of our solar system, and the use of powerful space telescopes to search distant star systems for exoplanets within the habitable zones of other stars are unfolding right before our eyes. Each new discovery not only brings us closer to answering these pressing questions, but also opens up new, unforeseen possibilities that could transform our understanding of life itself. The quest for knowledge about life beyond Earth is no longer the realm of science fiction. It is very much a present-day scientific pursuit, filled with questions that will shape the future of humanity's exploration of the universe. Throughout history, human activity has propelled our exploration and understanding of the universe, sparking an innate desire to ask questions that stretch far beyond the confines of our everyday experiences. From the early civilizations that gazed up at the stars with wonder, to the modern space agencies that now launch sophisticated spacecraft, our curiosity has always driven remarkable advancements in our quest to understand the cosmos. The invention of the telescope in the early 17th century was one of the first transformative milestones in this journey. This groundbreaking device allowed astronomers like Galileo and Johannes Kepler to observe celestial bodies in unprecedented detail. These figures shattered the Earth-centered model of the universe, giving birth to the sun-centered heliocentric theory, which fundamentally altered our view of the cosmos. These early discoveries set the stage for modern astronomy, establishing a trajectory for exploration that would only accelerate with time. The launch of Sputnik in 1957 marked another pivotal moment in humanity's journey into space, igniting the space age and signaling the beginning of space exploration. Soon after, the first humans were launched into space, and we took our first steps on the moon, sending a clear signal that our reach extended far beyond Earth. These milestones were not only scientific achievements, they were also deeply symbolic, embodying humanity's innate desire to explore the unknown. These accomplishments expanded our knowledge of the universe, providing insights into the complex systems that govern our solar system and revealing the profound beauty and mystery of our cosmic neighborhood. In more recent decades, the establishment of space telescopes like the Hubble Space Telescope has allowed us to peer deeper into the cosmos than ever before. Missions that have traveled to distant planets, asteroids, and even comets have provided us with invaluable data, enhancing our understanding of celestial phenomena that are billions of light years away. These instruments, coupled with advancements in computer technology, data analysis, and international collaboration, have transformed humanity's exploration of the universe from mere observation to a deeper, more comprehensive understanding of cosmic history. Yet, as we unravel the mysteries of dark matter, black holes, and the very nature of existence itself, one fundamental truth remains at the heart of our exploration: our place in the cosmos. Through all these endeavors, human activity has not only expanded our knowledge of the universe, but also reinforced our connection to it. Each new discovery serves as a reminder that we are part of something much larger than ourselves, igniting a shared sense of wonder and curiosity that continues to drive our exploration forward. This journey into space is not only about gaining a better understanding of the cosmos, it is also a means of learning how to protect our own planet. Space exploration often forces us to confront the challenges of sustainability, resource management, and environmental impact. The limitations of our resources in space mirror the fragility of Earth's ecological systems, prompting us to reconsider our approach to conservation on our home planet. For example, life support systems used in spacecraft have become a source of inspiration for sustainable practices here on Earth. These systems, which recycle air, water, and waste materials, demonstrate innovative methods that could be adapted to Earth's own environmental challenges. One such technology, the closed-loop water systems used aboard the International Space Station, could offer solutions for reducing water waste in arid regions on our planet. By applying these advanced techniques, we can develop more efficient and sustainable methods for conserving vital resources, ensuring that both our planet and our exploration of the cosmos can continue for generations to come. Moreover, observing our planet from space offers an unparalleled vantage point, providing a perspective that cannot be achieved from the ground. Satellites play a crucial role in monitoring the dynamic and ever-changing environment of our world. They track the alarming deforestation of vast forests, the shifting patterns of climate that threaten ecosystems and human livelihoods alike, and the rising levels of pollution in our air and oceans. By capturing these changes, satellites empower scientists and policymakers to make informed decisions, helping to mitigate the destructive effects of human activity. This bird's-eye view of Earth is more than just an observational tool. It paints a vivid picture of the complex interconnections between ecosystems, illustrating the delicate balance between nature and human intervention. It is a reminder that the actions we take in one part of the world can ripple through the global system, affecting biodiversity, weather patterns, and air quality. In this sense, the act of observing Earth from afar underscores the urgent need for a collective response to the environmental crises we face. The value of space exploration extends beyond technological advancements. It fosters a spirit of international cooperation that offers a powerful model for addressing global challenges. Just as space agencies around the world collaborate to share resources, knowledge, and expertise in the pursuit of interplanetary missions, this same cooperative mindset is essential for solving Earth-bound problems. Climate change, biodiversity loss, and pollution do not recognize national borders, and tackling these issues requires nations to work together, pooling their resources and knowledge. The lessons learned from space exploration, where countries unite for the shared goal of exploring the unknown, offer a blueprint for how humanity can join forces to safeguard the future of our planet. Space exploration, therefore, serves as a reminder that while we may be divided by geography or politics, we are united by the common thread of our planet's fragility and the shared responsibility to protect it. Human curiosity, an intrinsic force that drives us to question our existence in the world around us, is one of the most powerful catalysts for scientific progress. From the very moment we gain awareness, our minds are filled with questions. Where did we come from? What lies beyond the stars? What is the nature of reality itself? This insatiable desire to understand has been the driving force behind monumental advancements in fields such as cosmology, where scientists seek to unravel the mysteries of the universe's origins, structure, and eventual fate. Curiosity sparks innovation. It is the engine that pushes humanity to explore, discover, and create. In the early stages of human history, our ancestors looked to the stars not only as a means of navigation, but also as a source of inspiration and wonder. The celestial bodies guided them across vast oceans and served as the foundation for early myths and metaphysical musings. These rudimentary questions laid the groundwork for the development of modern science. As early astronomers observed the movement of celestial objects, they began to formulate theories, eventually developing methods of inquiry that would shape our understanding of the cosmos. The ancient desire to comprehend the universe gradually transformed into a rigorous, systematic exploration that continues to this day. The invention of the telescope in the 17th century marked a turning point in our quest for knowledge. With this new tool, humanity was able to peer deep into the vastness of space, discovering wonders such as distant planets, moons, and galaxies. Each new discovery sparked further questions and fueled our desire to explore more. As technology advanced, we were able to capture events like the collision of black holes or the birth of stars in distant galaxies, each new insight offering a glimpse into the universe's complex and mysterious nature. These discoveries are not merely academic. They are profound reminders of our place in the cosmos and our never-ending pursuit of understanding. At its core, our exploration of the universe is not only about uncovering the mysteries of space, but also about discovering what it means to be human. As we explore the stars, we are, in essence, learning about ourselves, our origins, our potential, and our purpose. The journey to understand the universe is simultaneously a journey to understand the very essence of life itself. In recent years, private companies have begun to play an increasingly significant role in space exploration, driving innovation and expanding the possibilities of our cosmic endeavors. Historically, space missions were dominated by government-run agencies like NASA and the European Space Agency. But with rapid technological advancements and growing public interest in space, private enterprises have stepped forward to take on a larger role. Companies such as SpaceX, Blue Origin, and Virgin Galactic are at the forefront of this shift, offering new approaches to space travel and exploration. These companies have developed cutting-edge rockets and spacecraft that can launch payloads into orbit at a fraction of the cost of traditional government-run programs. SpaceX, for instance, has already revolutionized space travel with its Falcon rockets and Crew Dragon spacecraft, which have successfully transported astronauts to and from the International Space Station. This shift towards commercial space exploration not only lowers the cost of access to space, but also opens the door to a variety of new business models. The rise of space tourism, satellite deployment, and the potential for asteroid mining are just a few examples of how the private sector is reshaping the future of space exploration. The growing involvement of private companies in this field also presents new opportunities for collaboration between governments, industry, and the scientific community, offering a new era of space exploration that is more dynamic, inclusive, and ambitious than ever before. As we move further into the 21st century, the boundaries of human exploration will continue to expand, driven by both public and private endeavors working together to reach new frontiers. Private companies are now playing a pivotal role in the realm of space exploration, working alongside government space agencies to achieve extraordinary feats like lunar missions and human expeditions to Mars. This collaboration, marked by initiatives like NASA's Commercial Crew Program, has proven to be a game changer. By combining the expertise and resources of both sectors, these partnerships are significantly accelerating development timelines, creating a more robust, sustainable approach to space exploration. What's truly groundbreaking about this alliance is that it allows for a seamless integration of public and private interests, an approach that transforms space missions once seen as exclusive to government entities. Today, companies bring a level of agility and innovation that government agencies can only dream of, propelling space exploration into a new era. In this dynamic landscape, possibilities that were once far-off fantasies are now becoming tangible realities. Commercial colonies on the Moon or Mars, once the stuff of science fiction, may soon be within our grasp. Fueled by rapid technological advancements and an evolving economic framework for space activities, these private enterprises are not just participating in space exploration, they are driving it. The involvement of these companies has catalyzed a new space age, one where the skies are no longer the sole domain of governmental agencies. The ripple effect of this transformation is profound, inspiring an entirely new generation of scientists, engineers, and explorers. These individuals, motivated by the vision of expanding humanity's reach beyond Earth, are looking towards the stars, eager to unravel the mysteries of the universe and perhaps discover new homes among the cosmos. Looking back at history, the human fascination with space is not a recent phenomenon. Ancient civilizations spanning continents and cultures were some of the earliest stargazers. For them, the night sky was not just a canvas of twinkling lights, but a vast, intricate map that influenced their daily lives. They were not only curious observers, but keen astronomers who saw patterns in the heavens that shaped their understanding of the world around them. From the Mayans in Central America to the ancient Greeks in the Mediterranean, cultures across the globe crafted elaborate celestial maps. These maps were more than just astronomical records. They were a fundamental part of the fabric of their societies. The movements of the stars and planets were imbued with deep meaning, influencing everything from agricultural cycles to religious ceremonies and governance. The Mayans, for instance, developed a highly accurate calendar system based on their observations of the stars. It was a tool that governed not just planting and harvesting, but also social and religious life. In Egypt, The alignment of monumental structures, such as the pyramids, with specific stars was a central aspect of their belief system. The Egyptians believed that the stars were not just distant objects in the sky, but were directly linked to their gods, guiding their souls to the afterlife. These celestial bodies were seen as powerful forces that influenced the very fate of the living and the dead. In the ancient city of Babylon, the connection between astronomy and everyday life reached its zenith. The Babylonians created one of the earliest known star catalogs, an achievement that laid the foundation for modern astronomical techniques. Their understanding of the planets, which they referred to as wandering stars, was groundbreaking. They realized that these planets followed specific cycles and, through detailed observations, began to predict celestial events with startling accuracy. This knowledge eventually gave birth to astrology, the ancient practice of interpreting celestial events to predict and understand human affairs. The legacy of these ancient astronomers is undeniable. Their contributions not only shaped their societies, but also paved the way for modern astronomy. The methods they developed, many of which involved intricate observations of the night sky, remain foundational to our current understanding of the cosmos. Their work continues to inspire contemporary scientists who now build upon these early insights as they venture further into the universe, expanding humanity's knowledge and exploring new frontiers. As we look toward the future, it is clear that the stars are no longer distant and unreachable. Thanks to the pioneering work of both ancient and modern astronomers, our understanding of the universe has never been more profound. What once seemed like myth or dream is fast becoming a reality, and the new generation of explorers and innovators stands on the shoulders of those who centuries ago gazed up at the night sky with wonder and curiosity, seeking answers to questions that we are still trying to answer today. The stars have always been part of us. Now we are reaching toward them more boldly than ever before. As we look up at the night sky, we are not merely observing a scattering of distant stars and planets. We are witnessing centuries of exploration, discovery, and deep-rooted curiosity. The myths and stories woven around these celestial bodies have profoundly shaped the trajectory of human history, influencing art, literature, and even our navigational techniques. From ancient civilizations to modern-day space missions, our relationship with the cosmos has been one of reverence, wonder, and relentless inquiry. Throughout the ages, the stars have not just been sources of fascination, but of inspiration. Early humans, in their quest to understand the universe, created elaborate stories and models to explain the movement of the heavens. These ancient attempts were not mere speculation, but the seeds of groundbreaking theories that would later form the foundation of modern science. One of the earliest models to emerge was from the ancient Greeks. In the 4th century BCE, the philosopher Aristotle proposed the geocentric view of the universe. He suggested that Earth was the fixed center around which all stars and planets revolved. This idea, though incorrect, became the dominant worldview for over 1,000 years, shaping medieval thought and even influencing the development of Western and Islamic astronomy. In the 2nd century CE, the astronomer Claudius Ptolemy expanded on Aristotle's geocentric model. His comprehensive system, known as the Ptolemaic model, introduced the concept of epicycles, small circular orbits within the main orbits, that were used to explain the apparent retrograde motion of planets. This model, encapsulated in Ptolemy's work Almagest, dominated for over 1,400 years, providing the backbone of astronomical study across Europe and the Islamic world. It was only when European explorers began to observe the heavens more closely that the foundations of this ancient model began to crack. The Renaissance brought with it a seismic shift in our understanding of the universe. The 16th century marked the bold and revolutionary ideas of Nicolaus Copernicus, who proposed the heliocentric model of the solar system. In stark contrast to Aristotle and Ptolemy, Copernicus placed the sun, not Earth, at the center of the universe. His work challenged not only centuries of astronomical thought, but also the Church's teachings, creating a dramatic rift in the intellectual landscape of Europe. This marked the beginning of the end for the long-held geocentric worldview. But Copernicus was not alone in this intellectual revolution. His ideas, once controversial, were supported and expanded upon by subsequent astronomers such as Johannes Kepler and Galileo Galilei. Kepler's meticulous observations led him to discover that planets move in elliptical orbits, not perfect circles, revolutionizing our understanding of planetary motion. Galileo, with his telescope, provided direct evidence of the heliocentric model, observing the moons of Jupiter and the phases of Venus, further solidifying Copernicus's theory. Together, these scientists laid the groundwork for a complete rethinking of our place in the universe. As we reflect on these historical milestones, it is crucial to understand that these early models, though flawed by today's standards, represented monumental advancements in human thought. Each step forward, each breakthrough was a giant leap in the intellectual journey toward understanding the cosmos. The process of learning from past theories and correcting them, refining our tools, and extending our observations continues to this day. Our current understanding of the universe is built upon the intellectual scaffolding of centuries of inquiry and exploration. The influence of celestial events on human culture is another profound aspect of our relationship with the cosmos. Ancient civilizations, such as the Babylonians and Egyptians, meticulously observed the movements of the moon and sun. These celestial phenomena played a pivotal role in shaping their calendars, agricultural practices, and religious beliefs. The regularity of lunar and solar cycles provided a way to measure time, and their observation allowed ancient societies to align their planting and harvesting schedules with the phases of the moon. Eclipses, in particular, have always been moments of awe and mystery. To the ancient Greeks, solar eclipses were seen as ominous signs, often interpreted as a battle between celestial forces. The philosopher Anaxagoras, in the 5th century BCE, boldly challenged the prevailing beliefs by suggesting that the moon was merely a rocky body that reflected the sun's light. This was a radical idea that laid the groundwork for later scientific inquiry into the nature of celestial bodies. Over time, eclipses became more than just portents of the unknown. They transformed into crucial scientific tools. In the early 20th century, British astronomer Sir Arthur Eddington used a solar eclipse to confirm Albert Einstein's theory of general relativity. By measuring the bending of starlight around the sun, Eddington provided direct evidence for Einstein's revolutionary ideas about the nature of gravity and the fabric of space-time. Such breakthroughs demonstrate how simple astronomical events, once seen as mere curiosities, have expanded our understanding of the universe and the laws that govern it. Today, solar and lunar events continue to spark curiosity and inspire technological advancements. Solar eclipses are broadcast live across the world, providing an opportunity to educate millions about astronomy. The study of lunar phases contributes to our understanding of tidal patterns and ecosystems, influencing everything from weather prediction to marine biology. The cyclical nature of these events offers insights not only into the mechanics of our solar system, but also into the intricate connections between celestial bodies and life on Earth. As we continue to peer deeper into the cosmos with modern tools like telescopes and satellites, we are reminded of how far we have come and how much we have yet to discover. The journey from ancient geocentric models to our current understanding of the universe has been one of intellectual revolution, each theory building upon the last. From the time of Aristotle and Ptolemy to the revolutionary works of Copernicus, Kepler, and Galileo, and onward to the groundbreaking theories of Newton and Einstein, humanity's quest to understand the cosmos has been marked by a relentless pursuit of knowledge. In the 17th century, Isaac Newton made one of the most significant contributions to the field of astronomy with his laws of motion and universal gravitation. His work unified the terrestrial and celestial realms, revealing that the same forces that cause an apple to fall from a tree also govern the motion of planets and stars. This was a paradigm shift in how we viewed the universe, offering a unifying framework that explained the movement of everything from falling objects to orbiting planets. The 20th century brought further breakthroughs. Albert Einstein's theories of relativity reshaped our understanding of space and time, revealing that gravity is not just a force, but a distortion of space-time caused by mass. This insight not only transformed the study of gravity, but also opened new avenues for the exploration of phenomena such as black holes and the expansion of the universe. These historical figures have done more than contribute to scientific knowledge. They have reshaped the way we see the world. Their work has inspired generations of scientists and dreamers to look up at the stars, asking questions and seeking answers to some of humanity's oldest and most profound mysteries. Today, with technology that would have seemed unimaginable in the past, we are able to peer deeper into the universe than ever before. What was once only the domain of myth and speculation is now a field of rigorous scientific inquiry, and the mysteries of the cosmos remain as tantalizing as ever. In our quest to explore the universe, we continue to push the boundaries of what we know. From the powerful telescopes that peer into the distant reaches of space to the satellites that orbit our planet, we are equipped with tools that allow us to unravel the mysteries of the cosmos. Yet, even as we make these groundbreaking discoveries, the universe remains vast, mysterious, and awe-inspiring, holding secrets that may take millennia to uncover. As we continue our journey through space, we carry with us the legacy of those who first looked up at the stars and wondered. The advent of advanced instruments has dramatically expanded the boundaries of our exploration into the cosmos, offering an unprecedented window into the universe. With the development of space-based telescopes, high-powered ground observatories, and sophisticated software, we are now able to peer into the depths of space with remarkable clarity and precision. These technologies, once the stuff of science fiction, are now revealing celestial phenomena that were once hidden from our view for millennia. Among the most groundbreaking advancements is the creation of space telescopes, with the Hubble Space Telescope leading the charge. Launched in 1990, Hubble has provided awe-inspiring images of far-off galaxies, nebulae, and other cosmic structures, freed from the distorting effects of Earth's atmosphere. This has allowed scientists to observe the universe across multiple wavelengths of light, from ultraviolet to infrared, unlocking new layers of information previously unattainable. Infrared telescopes, for example, have opened a portal into the cooler, dust-enshrouded corners of space, revealing star-forming regions and other hidden phenomena. Meanwhile, X-ray observatories peer into the most energetic and violent processes in the universe, such as the swirling matter around black holes or the explosive deaths of massive stars. These tools allow us to study celestial bodies in ways that were once impossible, bringing us closer to understanding the fundamental forces that shape the cosmos. Yet the power of modern astronomy extends far beyond just telescopes. The rise of computational astrophysics has transformed our understanding of the universe. Researchers now use supercomputers to simulate complex cosmic events, from the formation of galaxies to the intricate dynamics of planetary systems. These simulations, aided by advanced algorithms, generate vast quantities of data that scientists can analyze to uncover patterns, make predictions, and test theoretical models. Such breakthroughs in computational power are crucial to understanding the universe's structure, evolution, and the mysterious dark matter that permeates it. The hands-on data gathered by space exploration missions have further enriched our cosmic knowledge. Spacecraft like the Mars rovers and the Voyager probes provide direct insight into the planets and moons of our solar system. These missions have unearthed crucial information about the geophysical conditions of Mars, the icy moons of Jupiter and Saturn, and even the outer reaches of the solar system, as Voyager 1 and 2 continue their journey into interstellar space. Each mission adds a piece to the puzzle of our solar system's history and the conditions that might support life beyond Earth. Looking ahead, the future of astronomy promises even more profound discoveries. As technology continues to advance, our ability to probe the universe will reach new heights. Space telescopes, such as the James Webb Space Telescope, are already pushing the envelope, offering insights into the earliest galaxies and the formation of stars. But even beyond telescopes, several innovations stand poised to revolutionize our understanding of life and the universe. One such frontier is the rapid development of artificial intelligence, AI, and machine learning. These technologies are capable of processing vast amounts of data at speeds that far exceed human ability. AI is already being employed to analyze complex astronomical and biological data, helping scientists identify patterns and connections that might have previously eluded them. This has the potential to unlock the mysteries behind the formation of galaxies, the evolution of stars, and even the origins of life itself. Quantum computing represents another exciting possibility that could reshape our understanding of both cosmology and biology. By exploiting the principles of quantum mechanics, these computers can perform calculations at unimaginable speeds. This could allow scientists to simulate intricate systems such as the behavior of subatomic particles or the dynamics of molecular structures with unparalleled precision. The implications for astrophysics and biology are vast. Quantum computing could give us the tools to model complex events from the birth of the universe to the formation of life, offering new insights into the origins and evolution of both the cosmos and life on Earth. Space exploration technology itself is advancing at an astonishing rate. New propulsion systems promise to make space travel more efficient, reducing travel time and increasing our ability to reach more distant parts of the solar system and beyond. With these advancements, we are likely to gather more data on exoplanets, planets orbiting other stars, helping us identify those that may have the right conditions for life. Missions to Mars and the moons of Jupiter and Saturn could further expand our understanding of the potential for life in diverse environments, pushing the boundaries of what we know about habitability. At the same time, breakthroughs in biotechnology are changing the way we think about life itself. Gene editing technologies like CRISPR are already allowing scientists to make precise alterations to DNA, which not only deepens our understanding of biology, but also holds the potential for practical applications in space exploration. Imagine genetically engineered crops that could survive the harsh conditions of long-duration space missions, or modifications to the human genome that would allow us to endure the radiation and weightlessness of space travel. Together, these technological advancements offer an unprecedented opportunity to rethink what we know about life on Earth and beyond. As we continue to unlock the secrets of the universe, new discoveries are certain to emerge. Discoveries that may not only deepen our understanding of the cosmos, but also lead to the exploration of new frontiers in biology, physics, and space travel. The future of space exploration and our understanding of life itself is bright, and as we stand on the cusp of these breakthroughs, the cosmos remains a tantalizing frontier, waiting to reveal its secrets.